a PDF format or just a single file? Because it currently is links.
Yeah, I'm going to share with you right now actually a PDF which contains links to the material and also the schedule so that you can follow along, and then afterwards we can kind of compile it all into a PDF as well for you to do that.
Thank you.
Cool, no worries. So apologies if there is some bings in the background, but for some reason this room makes a noise whenever there is someone's joining the Zoom room, as you can hear here. So I'm not sure how to disable that. Hopefully it will only be at the start while we kick things off. So welcome everybody, and thanks a lot for signing up for this workshop related to Nextflow. So my name's Evan. I'll be the lead tutorial provider today, and then tomorrow we're going to kick off with some with Paolo, Tommaso, and Maxime, who I'll introduce now. So kicking things off. What is this workshop all about? So we're kind of going to mainly talk about Nextflow today. And Nextflow is a workflow manager. Hopefully you have heard of it, or at least are here in the right room to go find out a little bit about Nextflow. So we're from Secura Labs, and we're kind of a spin-off from a university who created Nextflow really almost 10 years ago now. And the basis of what we're trying to do with Nextflow is trying to solve the problem around data analysis pipelines, particularly in workflows, particularly in the scope of life sciences, genomics, and anywhere where there's got a large amounts of data. And we kind of see there's a kind of big problem at the moment that trying to solve here. And one of them is that these data analysis pipelines can become very complicated in several ways. One is the fact that there becomes very large number of steps. So we have pipelines who have 50, 60 different steps. Each step is a piece of software, a script, etc. And the other part of it is just the volume of data. So the volume of data means that we have to parallelize these pipelines and therefore run them in distributed systems. And the flip side of that is that these pipelines then require complicated infrastructure. So whether you need to run in a cloud or in a cluster, and managing that is particularly difficult in the context of teams and collaboration and kind of working in that way. So a little bit of background on myself. So I originally trained in biotech and have kind of made the switch over to bioinformatics just over 10 years ago now, and was sort of studied and sort of met my co-founder and the creator of Nextflow, who's also on the call here, Paolo Tommaso. And we kind of kicked off Nextflow. We were in a lab doing multiple sequence alignment. Our PI at the time, so Cedric Notre Dame, created some software called T-Coffee, which is a quite commonly used multiple sequence aligner. And the idea of the software was we were submitting a lot of pipelines to our cluster. It was like an SGE cluster. And we were kind of experimenting at the time of ways that we could first sort of share those analysis with other people, kind of run them in different ways, but also experimenting with the cloud. And this was very, very early on in AWS. And we're trying to think, okay, how do you take an analysis pipeline then and then run it in different infrastructure, which is very much the same problem as trying to share it with someone else who's got a different cluster or a different computer or even different operating system, and kind of taking those ideas and some very sort of nascent technologies at the time. So the likes of being very Git centric around, using GitHub for social coding and the use of containers. And those kind of ideas coalesce together to really lead to the formation of Nextflow. And it was a kind of a slow project, began very slowly over time, started to get kind of some organic growth. And then around 2017, we started to see, picking up an interest, and obviously now workflow managers have become sort of very popular in kind of ways to do things. And Nextflow in particular has, really risen a lot. And I really loved working with Nextflow. And at the end of my PhD, I thought I didn't really want to stop this. So we created Secura Labs, the company really just to, as an open core company, so with Nextflow at the heart of it, to build everything around that. And we also have on the call tomorrow will be Maxime Garcia from SciLife Lab, and he's going to walk us through the introduction to NF Core and the tutorial for that part, so how we can use NF Core pipelines, etc. Okay, I'm just going to shut my windows because it seems that the children next door have decided to come home. Okay. Apologies for that. Okay. So what are we going to go through? So I'm going to share with you straight after this, well, actually I can share with you now, this kind of schedule that we have and what we're going to go through. So we're going to start with just an intro, basically this part here on some slides. We're going to look at introduction to Nextflow, the kind of core components of it, so what makes it up. And then we're going to jump straight in and set up our environment. So the way we're going to do the majority of this workshop is we have a cloud environment which is pre-configured. So this is an interactive development environment. It's essentially a terminal in the cloud. And this way everyone starts with the same environment. So you just need a browser to be able to access that. We'll spend 10 minutes or so after this, set that up and get ready, install all the things that we need, and then kick it off from there. We'll start off with a first Nextflow script, and we'll kind of jump straight into understanding the kind of nuts and bolts without maybe understanding exactly what's going on in the background, but just to get a flavor of what's happening with Nextflow. And we'll jump into a 15-minute break. And in the middle section here today, we will build our own Rna-Seq pipeline. So we're going to jump straight in. You'll get sort of hands-on experience in building a simple Rna-Seq pipeline. Sort of 4 different steps: quantification, making an index, etc. And from the end of that, you should get a good flavor of sort of what Nextflow is about. And then for the final section today, we will be doing an exercise where we will build the container that we used to run that Rna-Seq pipeline. And this is kind of a general purpose in the sense that it's applicable not specifically to Nextflow, but it kind of gives you a concept of how these containers work. If you're already a container guru, maybe you want to skip that section, but and it's sort of the end of the section. But I would sort of recommend it if you're sort of new to containers or even sort of moderately interested, because we'll kind of dive in deep to what we're going to go through there. Then in day 2, we're going to jump in and sort of look at the more advanced technical syntax of Nextflow. So this is around what channels are, those are the things that we hold the data with, and the kind of core part of the data flow programming model. We'll look at Nextflow processes, which is the actual building blocks of our pipeline. This is where the tasks are defined. We'll see operators, which is where you can modify the data, which is inside channels. And then we'll go on and look at a section on configuration and deploying in the cloud. So the one part of Nextflow is very much around the syntax of how you write the pipeline. And the other part of it is really how can you run the pipelines. And we keep those things very distinct and separate for good reason. And then we'll finish off tomorrow with an introduction to NF Core and an NF Core tutorial where you can start running some of the NF Core commands, seeing how you can use those pipelines, maybe even think about if you're going to build your own pipeline in the future, kind of the standards that those the NF Core have created, and how you can leverage some of the tooling that exists already. Okay, so let's start off and think about what Nextflow does and also what Nextflow doesn't do. So we are really in the business here of pipelines and of workflows. And these are typically batch-like computation. So where you have multiple tasks, you have data which is going into those tasks, running through one or typically many different steps, and then producing some kind of output. And this is happening in a batch-like fashion. This is very different from something like our studio, say, where you're interacting with the data itself. It's not like we're going to jump into some interactive session, generate some graphs, etc. No, it's really running batch-like computation. And it's typically batch-like computation where you have distributed compute, where you've got many different tasks that you maybe need to farm out, maybe need to send to your cluster or send to your cloud, and manage it in this way. So this is a very typical kind of example, but this is very idealized. You can see here, this is running some GATK best practice pipeline. And this is kind of a visualization of what's happening, but in reality, these things are much more complicated than that. And if we look at, this is an example here from a genome parasite annotation pipeline. Each one of those circles there is a piece of software, and or a script. And you can see that the data has to have quite a complex path as it flows through the pipeline. So here you have 70 different processes, many different scripts, and then managing this becomes very difficult. If you want to pass that piece of software, if you want to say, hey, run this pipeline to your colleague on the other side of the world with a different machine, it's going to be very difficult to do. And this was the kind of the bane of bioinformatics that for a long time was the actual installation of the software. And I'm sure many of you have a lot of experience where you just, before you start the project, you typically spend a significant amount of time just setting things up. And containers and kind of one of the main things we do with Nextflow is really eliminate that. So it really has to be set up once, ideally by one person, and then once you're set up, you're good to go. Another thing you can think about is how do you bumper version of this. Imagine you just need to change one thing. How can you be sure that you're going to be able to do that in a kind of reproducible way? And that's what we're going to get to now. And this is how we sort of started, took the initial angle with Nextflow, was really around reproducibility. So if we think about some common things around these workflows and common problems that we typically all have in life sciences, one of them is that we are now having increasingly large data sets. And these data sets can be very, what we call kind of bulky. So they are typically long strings, which we're passing around to different tasks. They are, big, large sequencing files. They're not easy to deal with. It's a very different kind of approach than what you see with like ETL-like computation, where you're typically taking things from a database, et cetera. Here in bioinformatics, we're very file-based. And we also use a thing that's called embarrassing parallelization. And if you haven't heard of this, you'll be familiar with the concept. It's the idea that you want to run each of your samples over this pipeline. So you're going to be basically scattering your pipeline, and you want to say, okay, I want to run these same steps with all of my samples. And this means that you can end up with hundreds, or some pipelines we have people running over 1 million different tasks. And that kind of orchestration then becomes very difficult to handle. On the flip side of that is the dependencies. In bioinformatics, we use a ton of different tools, whether this is something I've taken from GitHub, maybe this is something I'm taking from a colleague, some scripts that I've written in my postdoc that I'm carrying around with me. Maybe this is things that even some proprietary software. I kind of need to pull all of that in together to develop my pipeline. And then from there, I need to be able to manage the dependencies. So all of the software which is relied on, those scripts rely on to be able to run. And handling that obviously makes our pipelines can be very delicate and very sort of difficult to manage. Here's a quick example of this sort of showing what can happen around trying to reproduce a particular paper. So this was showing it takes around 280 hours to reproduce a typical computational biology paper. And this is because even if you have the methods and you've got all the software numbers and all the versions, et cetera, it's still incredibly difficult to recreate. And you'd think this should be relatively easy nowadays, given the fact that everything is in silico and you should be able to describe the experiment successfully. It's very much akin to having all of the pieces of a jigsaw puzzle and being told, okay, the paper just says, okay, put this back together. Kind of assuming that the difficult part is the jigsaw puzzle, is the pieces, but actually the real difficult bit is the puzzle itself and putting that together. It gets kind of worse than that though. And the reason it gets worse than that is that because even the same applications, even if you have all the jigsaw puzzle pieces, and even if you put it together in the same way, you can still end up getting different results. And this is what we were able to show in the Nature Biotech paper that we released with Nextflow, that even in situations where you install all of that same software, you still get differences between operating systems. So in the top one here, I installed that same pipeline on Mac and on Linux, and we ended up with like the start location of proteins just being genes just being slightly off in that regard. Likewise, with very common software, so things like Callisto and Sleuth, there's a difference between running it on Mac and on Linux. You ended up with genes being called differentially expressed or not. And this is just me underlying differences in rounding or in the underlying libraries. But all those little differences over a huge pipeline, they kind of all add up. And they kind of end up with these kind of problems around reproducibility. Of course, we can kind of all solve this now with containers, but this is kind of one of the angles that we took on this. Reproducibility is really one part of it. And if you think about the title of this thing, we're going after fair pipelines. And as part of that, we kind of think there's also a wider aspect of this. And the way we like to describe it is reproducibility is one part, but we think just as important are things like portability. And this means that I can share with you my pipeline and that you can run it in a different environment. So you can take that pipeline off the shelf and launch it in any different run, and obviously still being reproducible at the same time. Another thing that's really important, we think, is scalability. This means I want to typically develop on my laptop or on my machine locally. I want a small test data set which runs where I can very easily develop this, share it around. And then when I'm ready to scale, I shouldn't have to change anything in the pipeline code. I simply point it to the cloud and some large data set or my cluster and XYZ, and it's able to scale up in this way. These pipelines also need to be validated, so we need to be able to track the outputs and sort of track the inputs and kind of do this, and it's very much related to reproducibility. And finally, usable. It's no good for you to create a pipeline that only you can use if you then need to share it with the world. It needs to be able to be used by people with all sorts of skill levels as well. I mean, now pipelines are being used all the way through from clinical applications, research projects. You want to be able to have people with, they say minimal, even command line skills to be able to run your pipeline. And at the other end, you maybe want to integrate your pipeline into some system with API calls. So being able to make them in all of this way is kind of ways that we can kind of simplify all of this and kind of the goals that we're working towards with Nextflow. Okay, so all of that was a kind of long-winded way to get to this point about what is Nextflow. So we've said before, Nextflow is a workflow engine. So it's a way of running pipelines. But there's kind of three main components I like to think of what Nextflow is. The first of it is it's a language. So it's a scripting way, it's a DSL, so a domain-specific language for writing pipelines. You take code in any language. So you can take your existing Perl, Bash, command line, sort of Python scripts, etc., and you wrap them up in what we call process blocks. You then link them together with data flow programming, with what we call channels, and you define the dependencies with containers, and all of that becomes a Nextflow script, becomes a Nextflow pipeline. We typically put that in a Git repository as the kind of the model that we use. And from there, once you have your pipeline defined, you can run it on any of the major platforms we support. So all of the major cloud engines, all of the schedulers that you're familiar with locally on your machine, Singularity, Docker, etc. So all of that becomes possible by writing your pipeline in a portable way. And the key thing is there's a distinction here between these two things. You really, there's absolutely no need in a way to, you should really write your pipeline once, and in theory, it should run on all these platforms. So keeping the distinction between the code that the pipeline defines, as well as the execution platform is really important. And that's the kind of the key thing which we're going to go over a few times today as well. So how does it work? Well, a couple of things here about why Nextflow is sort of different from any other kind of languages that you may be familiar with or things you may have seen in the past. One is it's a DSL. So this means it's a domain-specific language. You can access an underlying programming language underneath. So if you're in situations where you have to create your own custom function or write something independent, you're able to do that. Whilst obviously leveraging for 99% of your pipeline, the existing syntax, which makes it easier, which is kind of what it's designed to do. Okay. Other things it has is this parallelization model. This is what we call data flow, hence Nextflow, the name. And this is a reactive programming model. From a user point of view, this is the thing that takes a little bit of time to get used to, but is incredibly powerful. It means that all of your processes, all of your almost like tasks are sitting there waiting. As soon as they receive the input, they react. And it's that kind of model which flows through the whole pipeline, which makes Nextflow extremely powerful in terms of its scalability. It allows you to have this thousands of, or tens of thousands or hundreds of thousands of tasks just from a single runtime. We have a self-contained approach, and this means that each task lives in its own working directory. It's like you can think of each task as some sort of completely independent unit of compute. And this ended up being very nice for the containerized model, which came about sort of around the same time which we developed Nextflow, as well as the kind of batch execution in the cloud model, which is very much like this, where you submit these tasks as independent units of compute inside of a container. And they're kind of isolated from this regard. And the final thing here is this portability, the thing I stressed before about writing the pipeline once, focusing on the syntax of the pipeline versus the execution platform, which is handled by the configuration. What does it look like? Here's a typical example, BWA-mem. This might be something you'd write from the command line or something you might have in a script. Here you can see that we're aligning the sample on the reference and we're piping it to SAM tools to run. In Nextflow, we can keep the existing syntax. So we can keep the existing way of writing this pipeline. We don't have to re-engineer anything. We can simply define it by wrapping it in a process block. We specify the inputs. You can see the reference is here and the sample is here. So there's the two inputs that we have. Define the output. This is what we want to capture from this step, capture from this process. And then we have the script section. And the script section is identical from before. thing that maybe looks a little bit different here, and maybe you haven't seen before, is what is this genome_ch or reads_ch and bam_ch? Well, those are what we call channels, and they're the real key to Nextflow, at least in terms of the data flow programming side. Consider the BAM channel here. If we use that from the output of the align and it becomes the input of the index, this linking of these two processes makes it implicit the link between them. So as soon as the sample enters into this BAM channel, as soon as the align sample process is finished, the index sample step will automatically trigger. So it'll automatically trigger. So the index sample is kind of on the right-hand side is waiting for this input. As soon as it's received, triggers off the pipeline. And that kind of flows all the way through. So if we had, say, for example, the index on here, the BAM index here that we wanted to use, again, they would trigger off the next step, etc. Obviously, this can become as complicated as you want them to be, but their whole kind of model works in this way. You can think about the syntax as well as it's relatively designed to be used by scientists and engineers in a simple way. So you can write highly parallel scalable applications without having to know too much about what's going to happen underneath in the back. So this is a very kind of nice way to use your existing tools, to use all of the existing things that exist in bioinformatics or at the moment today, and really just link them together in a very scalable and parallel way. It also makes the pipelines really readable, so you can make it kind of quite easily see what's happening from top to bottom and understand how that all works. This is a kind of visualization here of what data flow is. So data flow programming is a whole kind of paradigm in itself of the way that you can write these pipelines. And these channels are what we call these data flow variables, and they're the real key here. These are, if you're into this, these are asynchronous first in, first out queues. So they're the things which link typically our two processes together. And they really shuffle the data or file paths or whatever we're using between the two processes. The way they work is as soon as a piece of data, say we call an element of a channel, enters into that channel, it's instantly read by the next step and then kind of usually triggers the execution based on that. And if we think about it in a practical sense, so imagine that we had this channel which contained 3 files, and we had a process which was going to run, say, a particular sample. So this was going to run fastQC, and we had 3 fastQ files in this channel. The fact that we have 3 elements in here means that we end up having 3 tasks being generated. So it's that kind of contents of the channel, the execution drives the execution. So this is the kind of data driving the processes here. In a more practical sense, if I had a process here, fastQC, which took as input the samples channel, the samples channel in this example has 1 sample. You can see it has just a single file, so sample fastQ. If I was then to change that and to say, okay, not just 1 sample, but all of the fastQ files inside that directory, in that case, then we would have the fastQC process triggering off the execution for as many fastQ files as there is. So this is like the implicit parallelization. So fastQC just runs completely in parallel there for the number of fastQ files that I have. Okay, there's another visualization of that, just kind of showing you that you get what we call the fastQC process, and then we would say as many tasks of fastQC. So you have a process, which is the definition of the that we're going to run, and then the tasks themselves are the different versions of it, so the different iterations as they go. You can also be in situations where maybe you don't have single files. You can have very complex data objects. So if I have pairs of files, maybe I want to handle them together. Like we're going to see quite a few times that we're going to have pairs of files that are based with a sample ID. And we want to process, say in this case, the gut samples together, and the liver samples together, etc. So we can create data structures inside these channels which contain like the sample ID and the 2 files. Keeping these things together, it allows us to have them used in the same way. Okay, so let's just consider a few sort of differences, because I often get asked what's the kind of differences between, say, something like CWL and Nextflow. So the main differences here is Nextflow is really, CWL is more of a language specification, so it's kind of a way of writing the pipeline. And then you have various different runners. Nextflow itself is both the language and the runtime. So we keep these things together. The other thing is like CWL is more of a meta language. So you're writing things in JSON, you're declaring these, whereas Nextflow is a DSL, so domain-specific language written on top of Groovy, which is a kind of Python, a Python version of Java almost. It makes it very easy to write. There's some things that you'll see. Hopefully, you'll see that Nextflow looks a lot more concise, and it's hopefully easy to read is what we're doing. And then also that Nextflow is really kind of community-driven here, based on that. Other things other people like to compare it to is things like SnakeMake. So these SnakeMake and Nextflow are probably the most similar of these in the sense that they're both DSLs. So SnakeMake's written on top of Python. The main difference here is that Nextflow is a push model. So this is this data flow model, whereas SnakeMake is pull, which means that you kind of have to write your targets first. So you have to think a little bit backwards about your pipeline, the way you do it. This makes some sort of differences around sort of the data structures, where Nextflow is not so kind of file-based, file pattern bound. So you don't have to have file patterns. It can use much more the data structure of the channels. Also information around the DAG itself, so when you have to compute that. And other things that we have is sort of different runtimes that we have there, and also kind of more sort of information on how you can launch it with Git, etc. Okay. So far, that's kind of all on the syntax, but I just kind of run through a couple of the deployment scenarios very quickly as well. So in Nextflow, you have a kind of local execution. This is if you just say Nextflow run. Running the Nextflow runtime will take your local script and deploy it either with or without container engine, if you wish, on the local file system that you have. In this case, each Nextflow task becomes like a POSIX process on there. What's obviously the most popular way to run Nextflow, particularly along to the open source community, is running in a cluster. And includes examples like Slurm, where Nextflow submits each task as a Slurm job into that cluster. And each of those then is be able to use the shared file system for the intermediate files. So when you have some input file, it's going to be taken from some shared file system, runs a task, and then puts the output back onto that. And then the next task kicks off. And this is kind of the orchestration that Nextflow performs. What's become super popular, and we'll see a demo of this tomorrow, is this Cloud Batch orchestration. And this is where Nextflow is submitting tasks to a batch system. For example, a good example of this is Aws Batch. And this is a great way to run in the sense that you don't have to buy any infrastructure. You simply spin up the resources in the moment, and typically using spot instances, which is about 80% cheaper than the traditional virtual machines here. And that basically spins up for the resources that you require, runs your jobs, and then spins back down again. This has become really popular for ways of running Nextflow. If you're really into sort of the details here, you can see that can be also quite efficient. So each job becomes like a Docker job onside those virtual machines that are able to run in that way. Other things about this is just the portability. So in practical terms, if I have my script, and we'll see this, what we're going to do most of the time, Nextflow runs locally on your machine. If I was to add some config, so in my Nextflow config, I'm going to add, okay, I want to run that same script, but I want to say run on Slurm with this queue, this amount of memory, etc. It's going to run on Slurm, and it's going to make each of those tasks request that amount of resources, etc. Put it on that queue. If I really wanted to take the exact same script and not changing anything now, I'm just going to change out here the executor. And Nextflow has the same concept here. I'm going to use Aws Batch now. The same concept of a queue and the same amount of memory, etc. It will translate all of those values into what's required from Aws Batch in terms of the API and submit that in that way. So all of that kind of comes together to make these pipelines extremely portable. And this is what I've stressed a couple of times, but it's that decoupling that makes it really important. Okay, getting towards the end here, and we can jump into some practical things. Containerization is super important for enabling that portability. So containers, they're very, very light. We'll see this at the end. They're very quick, can spin them up very fast. And that means that it has big advantages over virtual machines, which were typically used. Also, the tooling around containers with Docker, et cetera, has become very valuable for us to use. And if we think a little about when to use containers, and I'll show you this later on, but hopefully, from this tutorial, one thing you can get out of it is really understand and be able to use kind of containers always. Because think it's really one of the biggest transformations that happen, along with obviously workflow managers, etc. It's just workflow managers make it so easy to use containers that there's really no reason not to. A few things on Nextflow itself. So the last couple of years have been sort of dramatic growth in the project, and that has really come about not necessarily by things that sort of we as kind of maintainers or anything have done, but it's really been driven by the community. And I think that the core part of that has just been the development of many different pipelines from the community, and then making them available that have drawn people into Nextflow and made it very easy for them to take things off the shelf and use it. And obviously, a big part of that has been the NF core community. Other things that we have are things like editors. So if you want syntax highlighting for your Nextflow, it can be useful if you're thinking about continuing this later on as well. And our kind of sort of the main uses of Nextflow in terms of the kind of growth and people who are applying this, it's still very much in the life sciences here. But also we have for large pharma using it, people with large amounts of sequencing, etc. Traditional research organizations. We see a lot of startups, particularly in the US, in the kind of personalized immunotherapy space, so personalized oncology, etc. Large amounts of sequencing data, running production pipelines, cloud-centric, so it kind of fits very much with the Nextflow way of doing things. Okay, and we're going to see much more of this tomorrow, but so NF Core has been a big part of that growth, and both Sakara and the NF Core projects are, and Nextflow have been funded by the Chan Zuckerberg Initiative, really to kind of grow this aspect of it and to build these pipelines themselves and to really come together around sets of standards for doing so. And this really has been sort of a huge part of that growth. Okay. I think that's it for now. I will jump back into, and we'll see some more slides later on, but hopefully it's given you a sort of short overview of Nextflow, and we can dive in and sort of start to see a little bit of what it looks like. I'm going to first share with you a file, a sort of PDF, which has got all of the instructions that we're going to use right now. So I'm just going to copy that in my link, and I will also paste the instructions into the Zoom. So these instructions will be able to be used. So if you have, for example, you can download the PDF and use this later on, but you can also just say take those instructions themselves and run them. So hopefully you can see that. And the first thing I'm going to do is just paste the instructions in the chat as well. So first things here. And I'm going to walk you through this and show you how we do this now. So let's go into here. I'm just going to create a new window so I can show you this fresh, exactly what it looks like. So we are going to use, today, we're going to use a Cloud9 environment. And this is an environment inside AWS. And this environment can be used for any kind of development. But the nice thing for us is that we have a kind of way in here that can have a pre-configured environment so everyone can start from the same location and get kicked off there. So I think I've just forgotten the usernames. So each of you has a username that's been created for you. And you can see that the usernames I'm just pasting inside of this Zoom chat there as well. I'm going to walk through how you do this, and we'll go through this a couple of times. You only have to do the installation once, but the setup will do the same thing tomorrow in terms of logging in here. So I'm going to open a completely incognito window here so that you can see I'm starting from complete scratch here. Hopefully everyone can see my screen. And the first thing we're going to do is go to that address. There's a web address in what I just posted to you. And that is a location in AWS, which is going to allow us to log in to our environment. So I'm just going to find that from here. So I'm going to paste that into here. And you should get this screen here, this login screen. Now, what we want to do is we want to select IAM user, the first thing that you want to do. And then we want to put in the account number. And the account number is this 12-digit number starting with 195. And once you've got to that stage there, you should be able to press next. And this is the part where you put in your individual username. So I can see that, I've got one, you can see, for example, it should be something like, apologies for pointing out Chris, but it's the easiest name for me to pronounce. I'm going to say Chris here is the username, and then the password here is secret 123 exclamation mark, but it's with a capital S, and you can see that in the chat as well. So you go like this, sign in. And if you get to that moment, that's probably the hardest thing that we're going to do today, and to log in. So once you've got to here, you can select Open IDE, and that will pull up for you a terminal that's got everything in it. Okay. Exactly. So if you have logged into AWS previously, make sure you just log out of AWS before you log in. Another gotcha could be if you've logged in previously, you should go into select region, and we're going to be working today in EU Central 1. So if you don't see anything there, maybe you've previously logged in. Make sure you're in EU Central 1. This is the location that everyone has all of those has their environments. So when you open up the IDE, it will select that open for you, and you are ready to go. The next thing I want you to do is, once you're there, is I want you to go to Secure IO training. This is also in the first instructions actually of the schedule. I'll place that in the chat as well. And this is our setup instructions. This is an environment setup. What we're going to do here, this is really, so this can be used anywhere. So you can actually take this, sorry, there's a password here, it's in the thing, so it's secret 123 exclamation mark with a capital. So this setup here can be used in any, so if you want to use this like in 6 months time, you can do this. And the kind of key requirements are here for installing Nextflow is to have Bash, kind of typical, and is to have Java 8 or later. We kind of recommend using Linux or an operating system or Mac. However, I think you can use Windows with Linux for subsystem, but you have to obviously be operating in Bash there. The main setup here then for this workshop is that we're going to be using Docker, because we're going to use Docker for our container engine. But optionally, you could have Singularity or Conda as well, works just as well. And there's a couple of other optional things here which we're going to use as part of this tutorial. For example, the AWS command line interface, because we're going to launch into the cloud, which you would have to install if you were going to run this onto your own laptop. Okay. So the first thing I want you to do is to look at those instructions there, and we are going to run the following steps. And try and do these. Please try and do these in order, because if you mess up the order, it can be a little bit difficult. So, but we're here. We can here and help you out if you have any problems. So I want you to run the first command curl inside your terminal, and then we're going to run the source setup, and finally we're going to install Nextflow. I'm going to kind of run through this with you. I'm just going to log into my own account, and then we can do that. But if you can set up, you can run through 1.2, 1.3, and 1.4, and you're all good to go. It might take something of like a couple of minutes to do that. Okay, cool. So it should take about 2 or 3 minutes for the main command to run there, and that's the one which is just setting up the environment itself for running. Okay, so I'm just going to log in as before using. What will often happen is, and what's kind of nice about these machines is that when you're not using them, they shut down. So you really only sort of use them as they're going, and then it takes a few seconds, maybe up to a minute to connect every time you come back into them. So it can be useful for kind of development environment as well for that kind of work. Also, if you need to interact with AWS services, it can be useful in that regard. Okay, you can see my machine's just taking some time. If you have any problems, write in the chat as well. We can, got some people here who can help out. Cool. So what you see, and you probably figure this out, but on the left-hand side, you have a file browser. I like to kind of be able to view this by saying view and then saying themes and UI themes flat light here. So this is by going view themes, UI themes flat right. This just makes it a little bit better for me. I think it maybe makes it a little bit easier for you to see my screen as well. And the other thing I'm going to do here is just zoom in a little bit. So make things a little bit larger for us. So down the bottom, you can see we have a terminal. This is just like a terminal you can type in. On the top, we have a file way to edit files. File editor. On the left-hand side, we have a file browser. So if you would have followed through the instructions as before, just going to take the top line here, go into the training material, and say we just need to do this once. This is downloading our scripts. It's downloading all of the data that we're going to use over the next couple of days. As well as some examples and some material we're also going to use. And then going to run source setup all, and this is the one that maybe takes a few seconds to run. If you're interested, this is just running a script. You shouldn't have to do this when you run on your local machine. It's increasing the size of the disk on the virtual machine for us here. It is making sure that we have the right version of Java installed for installing Nextflow. It's also installing, I think, Docker. And it's also pulling this container that we're going to be using for the rest of the workshop. Again, not necessary if you want to do this on your own machine, but just a kind of way for us to all have the same machine that we use when we run through. Okay, and the final command that we're going to run there, and this is the one that you would run and typically install, is the way of installing Nextflow. So this is a curl command, which is just basically taking a script and passing it to Bash. And this means that Nextflow can be installed really as a one-liner, something that you can run on your own machine. And then finally, the one we're going to move Nextflow, so which is going to have been a file created, onto our path here, onto this bin directory, which means we can access it. And exactly like the question there in the chat about if you run this on your local machine, you don't have to run setup all. Exactly. So this 1.3, this setup all, is really just for AWS and for the cloud environment. Very much an optional thing to run there. Okay. So with that, if you're able to run Nextflow info and get this, that's what should have done the hardest part of the course. I'm onto the second to last layer of my container it's extracting. So hopefully I'm just a few seconds away. Maybe you can try raise your hand if you are successful to be able to install Nextflow. I'm not sure how you raise your hand. There, okay, I can see some hands raised. Great. Awesome, thank you. That's great to see. Good job, everyone. Awesome. So I'm going to install Nextflow now. And move it onto my path. And with that, we are good to go. Nextflow info, and we are good. Okie dokie. That was relatively smooth then. So congratulations, everyone. That's as I said, for sure the hardest part of the workshop we've got done now. So we're gonna start off now by looking at a first Nextflow script, and then we can take a. I think that's the schedule. We can take a break after that. And the first part of this is really going to be, I don't want you to focus so much if you don't understand all of it, because it's not necessarily straightforward. However, when we kind of go through this, I just want you to kind of think about the kind of main concepts that are happening. And it's going to take us to see a couple of scripts and a couple of examples before we try this. So we're going to run a hello world script. And you can see on your left-hand side, you'll have, and inside this directory, you have a script which is called hello.nf. So I'm just going to say to run it first, I'm just going to say Nextflow run hello.nf. And that's how we kind of get started. That's how we can run any Nextflow script with Nextflow run. And you can see we get this kind of this output, which tells us the version of Nextflow we've run. And then it says here some information basically around the processes which I've run. And it's printed this to the command line, to the terminal here, world, hello. Okay, let's dive and understand a little bit what's happening. So I'm going to double click on that hello script. And then I'm going to here shrink this down. And we're just going to have a look at a little bit about what's going on here. So I've moved this. Maybe we can make this a little bit bigger. So what is this script doing? Well, it has two processes. And the processes can be defined here, as you'll see that there's one process called split letters and one process called convert to upper. And ultimately what the pipeline is doing is taking a string, hello world, it's taking the string hello world, it is splitting it into 6 characters. So this is what the split is doing. And then it's converting those to uppercase. Now, the reason why we use this pipeline here, it's not really kind of doing anything too complicated, but it's also using tools that are very common. So everyone has these tools in Bash, so print, split, cat, and tr here. But also they're kind of like what bioinformatics does, is basically taking strings, putting them into files, manipulating them, and then generating some kind of output. So I want you to focus firstly on the 2 sections which are between these triple quotes. This is the real heart. This is like the bit that Nextflow executes. And we can kind of run through and see how would we do this pipeline without Nextflow? How would we take this part and run this separately? So I'm going to take this section here first. I'm just going to take this command here and see exactly what would happen. So it's going to run here, print F here, and then it's going to place this $X is actually going to be the string itself. We'll get to a second about the kind of full syntax here. So I'm going to place hello world here. I'm then going to pipe. So we're going to pass to this command split and this b.chunk. Don't worry if you've never seen split before. Split is just a software tool that takes strings and creates files out of them. So split is going to take our string hello world. It's going to take the first 6 characters, hello, going to put them in a file which is prefixed with chunk. The second one is going to take world and put it in a file which is also prefixed with chunk, but it's going to have a different name. So I'm going to run this here just in the command, nothing Nextflow here, launch this. And I'm going to do ls to see what's being created on this chunk. So what's happened is we've created now from a string 2 files, chunk AA and chunk AB. And if we look inside what's chunk AA, so go to cat on chunk AA, you can see hello. And if I do cat on chunk AB, I get world. So kind of pretty trivial, but the interesting thing here is that we've kind of created these 2 files, which we're then going to process downstream in another process later on. Okay. How does that occur though? How does that thing actually happen? So let's think about the next step, which is convert to upper. And convert to upper is going to take the chunk files. So it's taking, I'm just going to copy paste this here into my command. It is taking first chunk AA and running this. So creating hello, so it's just converted it to uppercase. And it's also done that in parallel on chunk AB, converted it to world. Okay, so hopefully you're semi kind of comfortable with the commands themselves, and you can kind of see, and now we can start to think about what's happening with Nextflow itself. So back to the script section. The script itself starts with the shebang here, which is saying it's a Nextflow script. This is optional, but sort of recommended if you want to run in different environments. The key part I want to start with is the parameters. Parameters are a kind of special scope in Nextflow, we call it, and we're defining a parameter called greeting. parameters are typically things that you want to change when you run your pipeline. So these could be input values, they could be files, they can be things which you vary when you run the pipeline. And it's often good to have an example pipeline, so an example parameter which just runs. So we don't have to even change anything in the pipeline. When we run by default value here will be hello world. It will launch through and we kind of know that the pipeline's run. So we first create a parameter called greeting, and that is in the first case, hello world. And in the second step, we have that the greeting channel, and this is our first introduction to channel, is simply the greeting channel itself, the greeting itself. So here is the string inside of here. Now, what is kind of going on here? Well, this is actually what we call an assignment of a channel. So we're creating a new channel called greeting channel, and that channel contains just a single string in this case. Pretty trivial, but it's a kind of the syntax that we use. Now, the important part is that we use this greeting channel as the input for the split letters step. So the greeting channel here goes into this process. The syntax here and the way you can read this is the input is a value, in this case a string, which we're going to give the variable x from some greetings channel. The order of this is that the split letters process will launch. It will then run printf where the $x now, you can see this $x, this x is the same as this x. So if I call this y, I should change this to y. If I call this, I can really create any name here. I can say some string, etc. And then I would have to put some some string here. So you've kind of got full options on what you do and what you call those. So when I have this here, this will run this section. And then the important part is at the end of that running, what am I capturing? What do I want to go into the next step? And here you can see that we're capturing any file which is called chunk_star. Remember, if we go here, if I go ls on chunk_star, you'll see that we get both of those files. So both of these files here go into this letters channel here. This could say letters. This is again a variable name that we're creating on the fly. Okay, so far so good. Let's now consider the next process. So the next process is going to take those two files and convert them into uppercase. So we're again going to start with what we call the file y. Again, if this was file z, this could be z here, whatever you want. And what I'm going to do is I'm going to say from the letters channel, flatten, I'm going to explain this in a moment, and then the main part is just going to be cat, exactly what we did before. Now the important part here and what the flatten is doing is that split letters is running once. However, convert to upper runs twice. And the reason for that is that split letters takes as input a single element, a single string, whereas convert to upper runs twice. It runs on every file that's produced there. Okay, enough about the kind of basics of the syntax there. Let's have a look at kind of ways that we can run this and what we can do with this one. So we've seen that file there. We've seen how that we can run it. I want you to observe a little bit about what happens if we run this multiple times. I'm just going to zoom in. I think we can zoom in one more. Maybe from here, I think. Okay, yeah, that's a bit better. Let's launch this a couple of times. So Nextflow run, hello. Notice the output here, world, hello. Run again. World, hello. Can run it again. World, hello. This should be like flipping a coin. I think we'll get there eventually. What's happening is that convert to upper step here is actually taking place in parallel. You can see now I've got hello world. What that means is they're actually taking place in parallel if you have In this case, we've got 2 CPUs, and each of those CPUs is operating on them perfectly in parallel. This means that in some cases, you're ending up with hello coming first. In other cases, you're ending up with world coming first. And this kind of, this model that Nextflow has of this parallelization being implicit, just coming from the fact that you have this channel model, means that parallelization is kind of, in this case, trivial because it's two files on our 2 CPU machine. But if we have 1,000 samples that we're going to launch into, and it's going to go across our cluster with thousands of nodes, that parallelization sort of applies at the same level there. So this parallelization is quite important, and you can see that we've already parallelized the pipeline simply by launching it in this way. Okay. Another thing that you'll notice is what's happening here with these actual numbers at the start. So you'll see here 34, A2, et cetera, and 16, 244, etc. These are what we call the hash, which is made up of the working directory. This is the location where each of those tasks is being run. And we'll see this in a moment, kind of why this makes sense and how this works. I want to now take my pipeline. I'm pretty confident, pretty comfortable with the way this is working. And let's say I want to now change something about it. I want to modify something the way it goes. Let's say instead of converting this to uppercase, I wanted to simply reverse the string. So I wanted to take it, and instead of converting it, I'm just going to say reverse that file. I'm going to save that now. Notice how I've only changed the second process and I haven't changed the first. And now I'm going to run the same pipeline, but I'm going to add on resume. I want you to take note of the working directories here. Those numbers, those hashes at the start. You can see the pipelines run, but the first one here, this 34A2, is exactly the same one as we had previously. And if you follow this line along, you'll see that it ran split letters once. You can see this 1 of 1, but it was cached. We didn't actually launch that script section again. Nextflow knew that it had seen it before. It essentially existed, what we call, in the working directory, and therefore it was able to cache it and skip the execution. And it knows, by looking at it, it knows that it's going to get to this stage and it's going to say, hey, that's not the same script section. In this case, the hash would be different, and therefore it's going to run that convert to upper, in this case, 2 times, and both of those will be fresh. This is very powerful because it means that you don't have to tell, say, to resume from a particular location. It means that you can really rely on the ability to resume the functionality, and so resume the pipelines from any location, and without, you can basically re-execute from scratch every time and run. So I'll explain this a few times. So the question is why did it cache? Well, the caching is it goes quite deep, let's say like this, but the way that you can describe it is that when Nextflow runs with this resume option that we applied, it's going to start from the top of the pipeline every time. And it's going to create what we call this hash, in this case 34 for this task. And it's going to see, okay, that task already exists. It's in what we call the working directory. And because it exists and the file has been generated or the output has been successful, it's going to skip it. So if I run this again, I'm not changing anything now, you'll notice that now, instead of just the first process and the first task being cached, the other 2 are cached as well, because in this case I haven't changed anything. But if I was to change even a single line here, so even something which doesn't actually make a material output, like if I just put an additional space before the split and I save, this actually is breaking the cache of those last 2 steps. So you'll see here when we run again that it's actually broken that completely. So you have to kind of be careful here with the way that you change those things here. Well, sorry, I changed that in split letters, so that's why it ran everything again. Let's change that in convert to upper just to be sure. That was my mistake. Let's run this again. Now, hopefully, if we're right, only this last two should be rerun. Exactly. Does that make sense? If so just write in the chat. We're going to see this quite a bit more in detail later on, but it's a really kind of important, really important point, and something that is a very powerful part of what we can do, of what we're able to do with Nextflow. Okay. Another couple of things that we can look at now is I want to now consider if I wanted to now run, say, with a different parameter. It's kind of nice that I had this kind of default parameter, but it's not particularly useful. Maybe I want to be in a situation where I want to change, just kind of revert what we've got before, where I want to change what the greeting is. I don't want to run hello world for the rest of my life in this pipeline. And the idea is we want to write our pipelines once, and then from there, we don't kind of want to change them too much again. So I'm just going to revert my changes, and I'm going to run the same pipeline now, but parameters themselves, in this case, params greeting, have got a special way that we can modify them. You typically may want to modify your parameter from the command line, like when I run this pipeline, run with these parameters. Or I may want to change them from some config, or I may even want to pass Nextflow some YAML file with all of my parameters in. And therefore, like parameters have got a special way of which we can deal with them, in which we can modify them without having to modify the Nextflow script itself. So I can say Nextflow run again, everything as I had before, Nextflow run, I'm going to say hello script. And now parameters have the special way of saying dash dash, so two dashes, watch that, greeting. And then I can put a new greeting. I can change what I'm going to insert here. So instead of hello world, I'm going to say bonjour le monde, like this. Now when we launch this, you can see that we have 3 of the convert to upper taking place. And that's because bonjour le monde, if you split it on 6 characters, ends up being split into 3 parts there. So you can see that this has been split and then it's just been split and then turned into uppercase bonjour le monde across those 3. Now, one thing I want to point out here, which can sometimes can trip you up, is that when you run with this is dash dash greeting. This is a parameter. This is a pipeline sort of specific option, something just for this pipeline. If I want to apply a Nextflow option, it's single dash. So Nextflow options like resume are single dash. If you want to change a parameter, it's double dash. And this is a kind of something which sometimes people are often running things like dash dash resume, for example, and getting caught up on that. So I'm going to say that again, and hopefully this should all resume from the beginning there. Okay, that looks pretty good. Okay, do we have any kind of questions on that section itself? Otherwise, we can dive a little bit deeper into what's going on underneath that. So put any questions that you have in the chat or shout out. I think we can definitely take some questions that you've got. Otherwise, I assume it's clear enough.
I was just wondering, will you also explain this flattened part later on?
Yeah, that's a great point actually. So if we think what's actually in this letters channel that we've created here? We know that there's 2 files. We know that we created chunk AA and chunk AB. What I'm going to do is I'm going to modify the script now. I'm just going to write return here. And this means everything after here is going to be ignored. And the reason for that is I just want to show you what's inside letters. And we can do that by saying view. What is actually inside this letters channel that we're running here? Let's go back and run without this. We'll just run without bonjour le monde, just with a simple example here. By viewing the contents of this channel, by kind of seeing what's inside of it, we can see that when we run this, we actually have the 2 files we expect. And I want you to notice that it says D1, E1, etc. and it creates these two files, chunk AA and chunk AB. They're somewhere pretty complex. They're like deep inside this work directory. And you'll notice this work directory is this full hash, which I sort of briefly explained before. And the reason is that this is this idea that Nextflow is self-contained in each of its tasks. Those tasks ran inside of that working directory. And it's from inside there that means that that's where the output files are as well. The point I'm getting at here is that what we've created, the way we describe this, is that the letters channel contains one element, in this case, but that element is a tuple. And that element is a tuple of files. And you can see that here by having this, when we do the view on it, we get creating return to us a single line, and it's inside these square brackets. And that square brackets is like, you can think of it as an array or a list or a tuple in this case. And that's kind of what we get. I want you to see what happens when I add flatten. I'm going to save that and compare. When we run with flatten here, you can see it's the same exact files, but now instead of being in a tuple, instead of it being what we describe as a single element made up of a tuple, we now have two elements. And this is really important for data flow because we describe it as it's the channel and it's the elements in the channel which drive the execution of the pipeline. Because convert to upper, the next downstream process, is just waiting. It's kind of like alive the whole time. So when we do this here, we remove this. Convert to upper is waiting for this files. And as soon as it receives them, as soon as it receives an element, it fires off the execution. Now in the first case, without flatten, it receives one element, so convert to upper runs once. When we use flatten here, we flattens the element out, and now it receives two elements, and convert to upper therefore runs twice. So just to show you this again, if I run this with flatten, so the default example, we can see that when it launches, oh, I must have, sorry, I just left that view statement in there, remove that. You'll see that when this launches, convert to upper runs twice because it's got both of those elements. Can anyone guess what's going to happen if I remove flatten here? Notice convert to upper, 2 of 2. If I launch the same thing, by removing flatten, it's only run once because it's received only a single element. So you can kind of think of it, the model is that Nextflow creates tasks based on the number of elements it receives. A little bit like we saw in the original example, if it receives like a single FastQ file, then it's going to run the task once. If it receives 1,000 FastQ files, it's going to receive them. It's going to submit 1,000 tasks. And that's the kind of main model of the way it works in this way. Is that kind of clear? A little bit clearer onto why we use flatten?
Yeah, thanks.
Cool. Okay, let's have a little bit dive a little bit deeper into resume and the work directory before we take a short break. If we consider now, I'm just going to remove the work directory here because sort of for illustration purposes, I've got a lot of crap in there now. Let's clear that. And I'm going to say from the exact same thing as before. I'm going to put flatten back here. Save that and launch. So the work directory is really where all of this, the work takes place. It's where each of those individual files take place. And as I said before, it's made up of this hash, which is typically unique. And if you change anything, then you change the file itself. Let's go inside there and have a little bit of a look. If I do, say, tree command, on work, CB in this case, 511, etc. If we do that in there, you can see that this work directory contains both of those files which just got created. if I was to run here, do the same thing now with resume, you'll see that everything will be the same and there will be no new work directories created because the whole thing is cached. So you can still see it's CB11, so I can run the exact same command. Everything is the same. If I remove that work directory though, so now I'm removing my work directory completely and I run the same command with resume, it's not going to be cached anymore because it doesn't have a record of it, doesn't have those files, and therefore I'm basically starting from scratch. So the work directory kind of holds our intermediate files, but it also kind of holds the state of the pipeline or the work directories that have been run before and the tasks that have been run before. Other thing I want to show you is if we have a look at now, not so much the first one. The first process is just taking a string, creating two files. What about if we consider the convert to upper, which now has a file, which is an input. Let's go tree on work. In my case, it's F4, etc. I want you to notice something about this file, this chunk AA in this case. Have a look here, and if you remember, chunk AA now, this is firstly a different color, but secondly, you see this arrow here, and what it's pointing to is the CB51142, etc. You'll notice that we're in the F4 work directory. We're in this work directory, but the input file is pointing to the other one. And the reason for this is that when Nextflow takes as input into a task, it doesn't have to copy the file itself. It doesn't have to take all of that file and put it inside that working directory and then run. What it's able to do is symbolically link the inputs from previous execution. So it kind of passes around this file object, and in this case, that file object is the path, which is simply symbolically linked into our new directory, and then it's able to use that as input. And that's obviously much more efficient for us if we have very large amounts of files or very large files, and we're operating in a cluster or somewhere where there's a shared file system. We don't want to necessarily transfer all those files around all the time and kind of move them between the location they live in and the execution environment. So this is another kind of useful mechanism that takes place in that regard. The final thing that I want to show you before we do this is that inside this working directory, we've seen that we've got the output files. And the one before, I showed you before that we had this one here, we've got the output files. We also have the input files, like this one here. It's got it as an input file. What about if we think about what else is in there and how is it able to keep that state? Well, we have inside that same location. I'm just going to do cat on the work F4. Don't worry if this is a little bit complicated, but it sort of shows you a little bit of what's happening sort of on the inside here. If I look at a command which is called .command.sh, this is the file this is actually the command that Nextflow ran. So Nextflow ran .command.sh in that location. And that location, you can see that in our case, this is convert to upper. This looks pretty familiar to this. So this here looks very familiar to our script section. With the one difference here is that the $y is actually, in this case, it's been substituted with the file name itself. Okay, and that can be super. That can be obviously very useful because what we're doing in the script section is we are mixing programming languages. We are mixing, in this case, y, which is a Nextflow variable. It's a Nextflow variable that we're able to then place inside of our bash script. This could be exactly the same if this was like some, if I was to do the same thing here, I could say, do this, and I would put, say, some Python here. I can then write some Python in this section and then put Nextflow variables in it as well. So it allows me to like mix up my programming languages very easily, and I can take my existing scripts, or I could call call those scripts as external scripts, etc., all the way through while mixing them with this $sign. Now, we'll see a few more examples later on exactly about the specifics of that and how you can do it, because you can end up with problems around having to escape variables, etc. But that can be all can be all handled in that regard. Okay, final thing before we go take a break, and there's another question there about what is the relevance of the name Ridiculous Clown. If we look, we can see here that when we run this pipeline, every time we get a new name, and this name is kind of like what we call a run name, and it's made up of an adjective. So just there's a whole list of adjectives in Nextflow it's going to use, and then it's going to take like a famous scientist, and then it's going to mix those together to create something which is mnemonic, something that you can remember. And if you say like Nextflow log, you can go back and you can see all of the previous runs that I've had here. So this is all the Nextflow runs I've just run today with you in this location, and then you have a kind of full history of what you've launched before. And that's going to be cool for being able to see, okay, what did I launch, and just have a memory of it. Though you have a kind of history of your execution, which can be particularly useful. But it also allows you to go and resume from a particular point. So I can say, actually here, I could say this was stupefied Baden. Not sure how you say that, but something like this. And I could go into here. I would say Nextflow run this command. And I could even say resume. And I could put in here a particular run. And then it's going to kind of use that work directory. Now, in my case, I've just deleted all my work directories, so it's not going to work. But if I was to say use the latest one that I haven't deleted, then you can resume from a particular run that you have. So that's kind of nice, another nice feature there for doing so. I think, okay, just check some of the questions here. So is the parameter in the script automatically the default? Yeah, that's a good question. So there's a precedence order here. And what I mean by this, and the question is related to, well, when I run here, and I said before, like when I use like Bonjour Le Monde, how does it know which one to use? So should it use Hello World, or should it use Bonjour Le Monde? And this is where it kind of comes into a precedence where it's the command line which overrides the script. So when we run here, let's see that Bonjour Le Monde is taking over. Now, the logic for this is that you can think about, you would have a parameter in your script which would basically apply if you don't apply a parameter. Imagine you have like defaults here, like params, something like, I know my default value for some alignment or step, some alignment value equals 5, you know, and then you always use 5 all the time. But then there's that one time that you need to be able to say, okay, I want to run this now, but I want to say, well, the default alignment value should change, or my alignment value should now be 10, for example, and then you're able to override it in there. There's also other ways which we'll get to later on, we'll see tomorrow, but you can define these parameters inside of config file. So you can have a Nextflow config, which we'll see later on for defining those variables. And you can even actually pass like a params file. And this params file can then have like a JSON representation of like greeting, bonjour le monde, whatever. And then you can sort of pass that. So a whole bunch of options for that. But I think we're kind of we're about on time there now we'll take a 15-minute break or so and come back. I think we had that to come back at 40. I'm not sure. So if you're in Europe, it's going to be, if you're on Central European time, it's going to be 6:40. So in 15 minutes or so, we'll come back and we're going to create now an Rna-Seq pipeline. So kind of build a pipeline from scratch where we're going to take the individual parts, build that up, and we'll kind of do some exercises together and jump into that. But I'll see you back here in 15 minutes. If you want to kind of take a look at that, and if you kind of want to take a look at more things here, we're going to be skipping forward to this section here on simple Rna-Seq pipeline. If you're interested in the kind of syntax of Groovy, if you kind of understand like this thing, you typically don't need to know much or if any Groovy to be able to write Nextflow pipelines, but you're interested in, say, for example, how the kind of basics of how you can do comments, etc. You can have a look at this section number 6 for understanding it, although it's typically not really necessary. I'll see you back here in 15 minutes, and we will go over section number 7. We'll start with building an RNA-Seq pipeline, and I'll see you in a moment. Okay, welcome back, everybody. Sorry, I was grabbing some water. I wasn't able to mute fast enough in time, but hopefully it wasn't. So we've got a few more people joining. Okay. So I wanted to jump in now and really kind of start with and kind of build a pipeline from scratch. And we're going to kind of build up the steps that we have for a pipeline. So we're going to start from, say, the early parts of it. We're going to begin from just building the parameter, adding our individual steps, and then launching there. So just a few more people joining. Okay. So I want you to jump ahead to section number 7 here. And what we're going to be doing here is building an RNA-Seq pipeline that is made up of 4 steps. And what's nice about this pipeline is maybe it's like a full production pipeline that you would run, but it's kind of enough to get you thinking about the different parts that you have when you have a pipeline. So for example, when you're scattering your samples themselves, or you're splitting them up, and you have to then, at some parts, you need to pull them back together again. And then you also have different parts where sometimes you run a single process, say, once, and sometimes you want to run processes which run on every single one of those steps. If you're joining now, I'll just point out, I will link to you some instructions which we have in the chat there. So just point over to the chat, and there are some instructions for how to access this material, for all of the locations of all of this. And we're going to be in section number 7, which we're looking at. So we're up to the part of building our own single RNA pipeline. So I'm just pasting, there's a PDF link there that you can follow along with. Okay. So what does this pipeline do? Well, it's a kind of a basic RNA-Seq pipeline. We're going to be using a tool called Salmon. And Salmon is a pretty popular tool for doing this RNA quantification, but it can basically use the transcriptome directly. So we don't have to have a kind of a genome itself. We can just align directly to the transcriptome, and it's also very fast. So it's a kind of a very quick way to take read data, so RNA-Seq data, and then convert that into some kind of quantification. We're going to create 4 steps of this. The first one that we're going to start with is creating an index of our transcriptome. And if we look inside here, you can see that it's pointing to a couple of the input parameters here. So we've got some reads files, we've got a transcriptome file, and we're going to kind of start with that. So if I look here, to begin the exercise, I'm just going to jump back into my environment. Can I clear all this? We don't need hello world anymore, at least not for this part. So I'm not going to save that. I just want you to look inside your directory here, and you can probably do this from the file browser. So from the environment tab here, you can see that you have this data, and inside this data, we're going to use this ggal, sorry. And that, if I do an ls on that data ggal, you'll see that there is some reads files. So if we do a cat on, or if we do a head on that, we'll see that the data itself, you can see that there's 6 files there: gut_1, gut_2, liver, lung, etc. And just to give you an example of what one of those looks like, if you're familiar with FASTQ files, you'll see here that you kind of have this section of strings. So it's a whole bunch of strings, and you can see that we have some identifier here. You can see this is this number, and then you have the reads themselves. So this is the A's, T's, and C's, big long string, and then you have the quality file, the quality number of that. And again, you have the same thing for each of the samples, and this is actually a cut down version. So it's basically some files which we know map to this transcriptome. And if we look at the transcriptome itself, so do the same thing here on the head of the transcriptome, you can see that this is just the first chromosome, and it's kind of one subsection, or one section, I should say, maybe of the chromosome here. I'm just done ahead on that, but we're going to find the locations of where those reads map to this transcriptome itself. Hopefully that's kind of clear enough. The real science is not super important in this part here. What we do need to do though first, before we start any of this, is to actually take that transcriptome, basically take this file here and create an index of it. And this is something that you will typically do once, or maybe you even have your transcriptome and you have your index with it. But in our case, we're going to run through that once. We are then going to take that index which we've created, and we are going to take each of the FASTQ files here, and we're going to map them to that index of that transcriptome we've created, which we're going to create quantification from that. We're also going to run in parallel some quality control on these reads to make sure that they're kind of fine. And then the last step, we're going to bring everything together and generate a multi-QC report, which can be used to kind of look at both the quantification step, but also the FastQC step. And that should kind of run through that. So the first thing we're going to do for the exercise is I'm going to show you on the left-hand side, there is all of the scripts here. So there's going to be sections where I'm going to ask you to do something and you can kind of do it along with me. But if you do get lost, you'll see that there is script 1, script 2, script 3, 4, etc. And that's really what we're going to be kind of going through together. So you can always, if you mess something up in your script, you can always go ahead to the next one and work through. So the first thing I'm going to do is start with script number 1. So I'm going to open that up here and have a little bit of a look of what it starts with. And this is something that you would typically have at the start of your pipeline. You'll define your parameters. You'll define your inputs that you want to use. In our case, as I said, we've got really 2 main inputs here: the reads. So we denote this because it's a parameter, something that we want to change. We want to write params.reads. And the thing that you might find a little interesting here is this base dir. And this base dir is essentially saying from the location where we're at the base directory of this project. This can be important. I mean, it also will work if you sort of leave this out. However, in situations, if you want to be really portable, you can be in a situation where you're running the pipeline, you're launching the pipeline from a location that's maybe not the project directory, in which case you want to have base dir in there. And it kind of just aids with the portability. I'll explain this later, but essentially if you run from GitHub, say the location of the files may be slightly different from where you're actually launching the pipeline. So in our case, we're going to have base dir, but we're going to point it towards this ggal samples, these chicken samples. And you can see here that we've got you've got *_12. I'll come to this in a moment when we come to use this. This is a way of capturing, this is a way of defining that we want to find all of the samples which match this thing, in this case, gut, liver, or lung, and then look for the first and the second read of those. The second part is the transcriptome, and the third part is just a multi-QC report, multi-QC location, which we're going to have for later on. What we're doing when we run this, so even though there's no process here, even though there's nothing, the script is not really doing anything, we can still run Nextflow run script number 1 and just make sure that you can just confirm that you can launch that. So I'm going to say Nextflow run script 1, and you can see that it prints here. It's just doing a print line of that reads, and this parameter reads is being changed there. Okay. First thing I want you to do is, and I'll just give you 30 seconds or so, I want you to make sure that you can run script 1. And then I want you to try and run script 1 and put some different value in for reads. So imagine that these reads run with default, but I just want you to try and run by saying Nextflow run script 1. And then I want you to change the parameter here, reads, to something else. It doesn't have to be an actual file. It can just be something you've got. So I'll leave you a few seconds to do that. And you can probably see from the example before, remember how we had greetings, which was -- greetings, and we could change it. We can do the exact same way with some with some other inputs. So we can say dash dash reads, and I could say, you know, some reads and star fast queue, for example. And this would then modify that reads. And then when I print this, when I run this here, it's going to print this to the screen. And I'm going to see that I've kind of overridden the default parameters which exist there. Now, there's a couple other exercises that I want you to look at. And these are here over in 7.1.1 and 7.1.2. I want you to now create here a fourth parameter. And I want you to define this parameter to be a place that we're going to store our results. And it's going to be a location that we're going to store our results, which is going to be called a parameter called outdir. And the next thing I want you to do, I want to make this message a little bit more intuitive, maybe something that says a little bit more about the pipeline name, maybe the pipeline parameters themselves. And if you look at the examples here, you can see that in 7.1, 7.1.1, 7.1.2, there is an example here which you should be able to kind of copy paste in, and then just have a little bit of a look at the recap here before we jump into actually our first process itself. So I'm going to give you a minute or two, say 90 seconds, just to run through 7.1.1 and 7.1.2 that you have there. If you have any questions as well, please feel free to jump into the chat or shout out.
I don't understand the first one.
Yeah, no worries. We can go through together. If we look at that, the first one is kind of saying we've got 3 parameters so far, and we want to add a 4th one. So that one is going to be called outdir. It's basically the output directory we want to create here. And we want to use it as basically a location where we store the results. So far, all of our results have kind of been going in these work directories, but we kind of wanted to specify a place that those results will go. So we could go in here and create a 4th parameter. And then we could say params.outdir. And here I'm just going to say results. And it's really kind of as simple as that. It's just a kind of a location that we can parameterize so that we can change in the future, but we'll kind of by default, we'll have a results location that we have there.
Does it matter the single quote versus double quote?
In this case, absolutely the same. Yeah.
They're the same, okay.
Yeah, so the double quotes will be if you need to use variables like space dir. And the single quotes that we're going to use are just like a simple string, no variables. Okay, so following through from the example here, we've seen 7.1.1. If we look at the example here, you can see here that this is just another way of printing to the screen. So we can use this log info. And here we've created, like, say, the name of the pipeline, printing out the transcriptome, the reads, and the outdir parameters. And then we're just stripping that line. So we're basically making it easy to read. And this is something that you can, quite easily, oh, that's the wrong one there, easily kind of replace from your pipeline. You can kind of make these messages as complicated or as simple as you like. It provides just a nice way. And the good thing about this is that this will also go into the log as well. So you can, if you go back after your pipeline is run, you're able to view that. So this was kind of just trivial. The point was that we can see that we can run with changing some parameters if we want. We can define new parameters, which we can then print here, and you can see that this kind of prints the message in a kind of in a nice way to see. We can also see there that we have been able to pass different parameters from the command line and how we can define those, and that we can use these kind of multi-line strings. So that's exactly what's happening there with that, with this one around this this triple quotes here. You can see that this is all a multi-line string that we're putting in there. Okay, let's start to do something a little bit more real though, and start to do some real bioinformatics. So this is just kind of a little bit of boilerplate that we've created in our pipeline, but something which has given us something nice. Let's go on to script number 2 and start doing some real bioinformatics. So I'm going to close this script number 1 now and open up script number 2. And you can do the same. And when you see script number 2, the start of it is all the same. We've actually just added in this comment for the pipeline parameters now, so you know what's going there. The interesting part now is that we've got our first process. And our first process here has this, this index itself. So it's called index, so it starts with process, then the name. It has one input, one output, and a script section. Is there a question? Is it HK?
Yeah, Evan, just a quick question. So is the base dir automatically defined, or that is defined at runtime?
Yeah, the base dir is taken from the project base directory. So in this case, in most cases, it's going to be the same as where you run the pipeline when you're developing locally, but it makes a difference when you run. I'll show you at the end of this exercise, we're going to run, basically we're going to run this pipeline directly from GitHub. And in that case, it can be slightly different because where basically these files will be in a Git repository, and where we run the pipeline may be a different location. So that's why base dir makes a difference. For us, it's exactly the same here.
But it is not defined. So if I try to echo it, there is nothing in base dir in this environment.
Yeah, this is not like a variable defined in your environment. This is a Nextflow variable, a special Nextflow variable.
Okay, thank you.
Cool. Okay, so we've seen this very basics of this process index. So it's got an input, an output, and a script section. Let's start with what happens first, which is the input section. So we are using, and remember the purpose of this is we're going to take our transcriptome, which is a big FASTA file, just a big string of letters, and we want to convert it into a binary representation of that. So it's an index, which we're going to use this tool 7 for. So we're going to take as input, and what we're going to define is we know that this transcriptome file is a path. So a path or a file can be used interchangeably here, but it's not a string. It's actually the path itself, the thing that we want. And we're going to say, where is it coming from? Well, we've defined it above is this params.transcriptome. So this here, whatever we define here, is going to be our input. In our case, it's a FASTA file that we're going to be importing. Then Salmon's going to run now. And Salmon is a tool for doing this quantification, as I mentioned before. And the command here, obviously this is specific to the tool, but it's Salmon index. We see this threads task.cpus, which I'll leave till later, but it's essentially a way to define the number of CPUs we want to run when we run the script. We have -t, which is the command in Salmon for providing the transcriptome, and -I, which is the location of the index we want to create. It's kind of like the output in this example. So going back, the important parts for us is we are running this command Salmon index, $transcriptome, and the reason it's $transcriptome is this is a Nextflow variable. And this Nextflow variable is defined here. If I was to change this to, imagine I called this like just transcript or something like this, I would then have to change this to transcript here. So the fact that this here is a variable means that we can call that transcriptome. And then the other interesting part here is that we are creating this index, and this index is the output. So it's basically saying, run this task, create this index, and then as the output, capture that index. I can see other hand raised. The question?
Yes, I was just wondering whether in the input directory, section, whether we can say file instead of path, like how we were doing it in the Hello World section.
Yeah, in this case, it's actually very similar. So file and path are almost interchangeable. There's one subtle difference in them, which we'll see tomorrow. Path has a way of automatically handling paths to a certain extent, and it kind of automatically turns it into a path. Whereas if you use file, you just have to use one extra transformation here, is that when you use file, you convert the string into a file object first. Whereas path, and sort of path is the way I'd recommend to do this, is it just converts anything that looks like a string basically into a file object. Just a subtle difference there. We'll see tomorrow why it's important, because there's a huge difference between passing around a string and that string being like, the name of your file, and a file object. And the reason being is that when you run a distributed system, you can't rely on the fact that you can just put a path, just put a string which contains the file there, because it's not necessary that the computer that's going to run the task has access to the shared file system. In cases like in the cloud, you need to transfer that, or Nextflow needs to transfer that file first. So creating what we call file objects, or in this case, like a path object, is really important. And it's kind of the key difference between this and doing this, which is the kind of main two qualifiers that we call them.
So you're saying avoid using absolute paths for pipelines. Is that what you mean by that?
Yeah, exactly. So let's say like this: when you input this here, you will create this here, and this is a string still. It's still a string. When it gets to here, though, it gets converted into a path, and this is quite interesting. So when we look at what actually happens here, Nextflow will stage that file, so it will symbolically link it into that location. So transcriptome here will not be the full absolute path. Transcriptome will just say the name of the file, because Nextflow's already handled it for us. I'll show you the example as soon as we run this. It'll be much clearer. Okay, I'm going to save this here, so I really haven't changed anything yet. And the key point, we're going to capture this index on the way out. Okay, let's launch script number 2. And we run this, and we get this error. And the error that we get is that salmon, the command, has not been found. Why is that the case? You can see that the actual command it tried to run, I remember it's trying to run inside this working directory, is salmon index threads. So you can see task.cpus became 1. T transcriptome.fa. So the faster file was placed, was kind of substituted for our transcriptome variable, and it tried to run index. But the error here, salmon not found. Why is that? Well, if I try and run salmon here, I get the exact same error. In this case, salmon, the command is not found because we don't have salmon installed on this machine. And this you think is a bit of a problem, but this is where we start to see kind of the benefits of being able to use containers. And instead of having to install salmon on this machine to run this tool, we can simply point it to a container which has salmon installed already. And to use a container in Nextflow, we can take the exact same thing. So Nextflow run script 2, and we're just going to say with Docker. And in doing so, we're now going to be able to run this command. So this task will now be run as a Docker run command. I'm going to try that. So run Docker run. Sorry, Nextflow run script 2 with Docker. And you can see, almost like magic, we've now been able to run that command. And something different happened here. We've actually, this salmon index did not launch in this machine. It launched inside that container. And I don't want to make it too much magic. So like the question will be, you'll probably have is which container did it use and how did you specify that? Well, the purpose is not to go too much deep into the Nextflow configuration, but if you look inside a file here called Nextflow config, we'll cover much more of this later, you will see that there is a container which is called Nextflow Rna-Seq, and this container actually has those tools installed, so the tools that we're going to use for this pipeline. Alternatively, you could say Nextflow run script2 with Docker and actually provide the name of the container. This is the equivalent. And then all of the tasks now are going to launch inside of that container. And very, very quickly to kind of show you sort of the difference here, if I say Docker run TI, we're going to see more of this later on, but if I run interactively on this container, and if now I say, so now I'm inside the container, and I'm going to say Docker, sorry, not say Docker, I'm going to say Salmon. You can see that Salmon is installed inside this container. If I exit the container and run Salmon, I don't have Salmon. So very kind of quick intro into this. Okay, so this obviously some questions. This is it a single container for the entire pipeline, or can you have multiple? You can have multiple containers. So far, I'm just showing you where we'll just have a single container for everything, but you can have multiple containers. You can define them dynamically, different processes, etc. And another question is, do the different Nextflow jobs reuse the same container, or does every process pull its own copy? So in this case, it's actually, it's going to have, we've only pulled the container once. So it's pulled the container once. We actually did that at the start. We can see this if we say Docker. And then you can do this on your machine. If you see Docker images, you'll see we've just got this one container. So we don't pull it every time. In this case, we just pull it one. Another question is, but isn't it going to keep downloading the Docker? So it just needs to dump, as I said, it just needs to download it once. And from it once, this essentially is able to run on that. So you can reuse and you can run 1,000 containers, sort of based on the same image. Okay. Let's kind of continue on the exercise a little bit. We'll see much more of this later on about what we can do with Docker and how that can run. Okay.
That may be beyond my abilities at the moment.
Oh, that's Siri. That's not sure where that came from. It's the Mac keyboards has Siri too close. Okay, so I want you to now kind of look at a couple of exercises here and how we can sort of use this in a different way. So I have
Evan.
Yeah, sure.
Yeah, just let me interrupt for a second. So the result of our step 2 went into the work directory. Where did it capture the index? Because I don't see it on the in our present directory.
Okay, so let's have a look. The question is, where is this index file? So this index was supposed to be created here. Where is it? Well, we can go here and we can say, firstly, let's just let me rerun because we've done a lot of things. So let's just rerun kind of default one that we had. So script2 with Docker. And this launches, and you can see it has the 7D1515. So it's got this work directory. And remember, I was saying that index now that we've just created should be in that location. If I was to say, there's a couple of ways I could do this. One would be to say, okay, what does the index channel contain? So I can say index channel view the contents of the output of this process. And launch that. And in this case,
okay, so in this case, the results is actually a Nextflow variable. It's not a real directory.
No, it is. It is. So in the first case, you can see that the index contains this file. Well, this is actually a directory, but there's this directory inside here. So notice the work 0437. If I do tree, let's say, on work 0437, you'll notice that here, there's the index inside of that work directory. Is that the kind of question?
No, I think I was actually, if you scroll up a little, the log that you're printing has out they're going to results. So out there says results.
Oh, okay,
So
yeah, yeah. So we haven't added in the outdoor part yet. We'll add that in later on as we go.
Oh, okay.
You're right.
So
you're right.
It's just printing it. Okay.
It's just printing for now. We're gonna bring that in when we think about what we call publishing the results later on.
Thank you.
But that's brought up a good question though, and something that I wanted to show you. So remember that this process now has an input, this transcriptome, and it has an output, this index. If we look at the work directory here, you'll see, and I'll just make this a little bit bigger so you can see it at the same time. You'll see it has these two things. Inside this work directory, there is the index, which is created from the salmon command, as well as the transcriptome. And notice the transcriptome is, again, the symbolic link. So it's actually just linking the full path here. And this is kind of the question about before was, should you use full paths? Well, in Nextflow, you shouldn't, it doesn't really matter. You should specify at the start the actual location of the file, and Nextflow will take care of it for you. So Nextflow will know it basically, when it runs that command, it will just simply use transcriptome faster file here, and it will kind of handle the full path aspect of it for you. Okay. So I want to now do a small exercise to kind of get a little bit familiar with changing some of these things. And the first thing I want you to look at is inside these sections here. So we've looked at Docker, etc. I want you to now first, instead of having to write with Docker every time, this is something that we can change in the config. So what we can do here is modify the Nextflow config file. And I want you to do that by adding this line docker.enabled equals true. This means that we no longer need to specify with Docker when we run this pipeline. I want you to, like I've done before, I want you to print the output of the index channel and then just run a view content. So basically do a view of the channel. And I want you to do a tree command of your work directory. You may want to remove it beforehand before you do this, but just to understand a little bit and look at your work directory versus kind of what's been created, and sort of understand a little bit about how it runs. So I'll give you a couple of minutes to do that, and then we will jump into talking about the read pairs and how we can deal with pairs of FASTQ files. Time is up. I'll just try and use the timer to keep me focused on that. So we're going to do a couple of things now. We're going to, as I go before, the first thing I'm going to do is add in this Docker enabled section. So I'm going to open up my Nextflow config file. And you can see here that we have a couple of things. They're kind of both related to the container that we're going to use and then the Docker run options. We'll see this at the end of today, why we need this run options, but I'm just going to add a line Docker enabled equals true and save that. This means that I no longer need to have, when I run this with Docker, so I can just, it basically means that Docker is going to be applied by default when I launch this. The next thing that we're set up to do inside of that exercise was to be able to run index channel and kind of do a view on that. So we saw that before, but just recapping, this index channel is going to emit the contents of that. So by writing index channel view here, when we run that, we print to the screen the index. And view is very useful for debugging here. It's kind of a very quick way to understand exactly where the files are that we're creating in particular, or what the structure of our channel is. And we'll see that a little bit later on as well. And finally, we can run tree on the working directory. And by doing that, we can see the kind of full structure. You can see I haven't deleted it for a little while, so there's all this, all of the files that we've got from running before. Okay. Now let's think about how we can start to use the actual read files that we have. And I want you to look at, open up script number 3 now. And script number 3 has the same top section that we had before, but we've removed the index now just to simplify it, just to explain a couple of important concepts. So everything is the same in the parameters and the printing line here. Now we want to, say, take these read pairs, and remember this is still a string here, but we need to convert it into something which is useful. So there's a couple of ways of what we call channel factories, or ways of building channels in Nextflow. And these are, if you're sort of interested in the specifics here, I should have pointed this out before, but if you go into the Nextflow, Nextflow docs, it's an unfortunate typo there. We can have a look, and you can see here the actual processes that we have. We're looking at now channels, and we are looking at channel factories. Yeah, so we are looking at some of these several ways to build these channels. We saw before the really basic ones. So we saw how we could create a channel here. You say sort of channel dot from, and this, so you can put basic ones. Okay, I create a channel with 3 elements, 1, 2, and 3. Basic enough. Also, something that we see quite a lot is actually, instead of just putting values in there, like simple data structures, integers, strings, etc., we can also create them from files. And the main way for doing that is by doing what we call from path. And this is this one here. And I was sort of hinting at this before, that there's a big difference between a path, so actually, and a string in this case. So in this case here, if we look at this read pairs channel, if we view it, in one case, using from path, you can see that we have what's called a file object. So I'm going to run through this. Nextflow now runs script number 3. And now it's going to take everything which matches here. In this case, it's just the first 2 samples. And these are full file objects. Why is that important? You can see that it's converted. I didn't actually give it the full path, but it's converted it into the full path. And that's because it's kind of knows exactly the location of that file object. If I was to treat this here and just say from, so instead of being a path now, I'm just literally just got the, treating it like a string, you'll see that kind of nothing really special takes place, and it's really just printed from the string here, which is not going to be useful for us. I'm going to modify this a little bit. I'm just going to say star here. Why do we want to sort of use this other one? So if before I had like from path and that kind of put the full path, what if I wanted to actually have pairs of files? And this is the special one factory that we have, which we call from file pairs. And it's able to take pairs of files and essentially, as it says, kind of take those pairs of files and treat them as a single element in our channel. This is kind of important. So if I'm going to run this now, say this, I'll just run this actually. I'll go back. I'll just run this on the gut example. So this here is the input, launched on this, and we'll see what happens. What this returns here from file pairs, confused there. What this returns is slightly different from what we've seen so far, because when we had our index, say, it was a single file. Or when we had our original hello world greeting example, we had each element in case was a string, hello world or bonjour le monde. In this case now though, the object, the element that we have is actually made up of a tuple. This tuple is made up of the sample ID and then the 2 files themselves. And this is exactly what this from file pairs does. And I'll just copy this down so you can see a little bit about how it works. What from file pairs does is it finds the kind of the matching part here, and then it's going to make an iteration on that. So it's going to look for gut_1 and gut_2, and it's going to treat them as if it's the same file. What we can do is change this gut and to make this like star, so that now it's going to match everything. It's going to match gut, liver, and lung. And it's going to create for us now, instead of a single element, we're going to get 3 elements, each one being the sample that we want. So we get an element for lung, an element for liver, and an element for gut here. This is very powerful and it can provide a way. I mean, you'll see much more of this tomorrow, but it doesn't have to be pairs. You can also decide if you have like triplicates of files, you can say something like size 3. If you want to include hidden files, for example, you can say hidden is true here. So you have a whole bunch of options, and those are kind of I'll leave for tomorrow, and you'll sort of leave for the different options that you have here in the documentation. For our case, and for our kind of purposes here, we are going to create this this channel, which is going to contain an element for each of our samples, and then we're going to run through on that itself. So I want you to make sure, I want you to kind of add a couple of things in here. Firstly, I want you to take the original script number 3 that we had. So this is the original script 3, and I want you to run it through. So save this. Your one will start with gut. And I want you to run this here. In the first case, it runs like this. I want you to modify the reads so that it runs with all of the samples. And you can do that either in the script or from the command line. Remember, we can modify any parameter from the command line. Next up, I want you to be able to look at the exercises there. And instead of using read pairs channel equals, I want you to use the set operator. And this is like one of the first operators that we see, but it's a kind of alternative to doing this variable assignment beforehand. And the final thing that I want you to do there is be able to use the option check if exists. You'll have to look up the documentation here. But check if exists is a powerful way to confirm that your channel actually contains something before you launch the pipeline. It's very easy to make typos in bioinformatics and we're kind of running stuff. It's very nice to actually make sure that when we run something that the pipeline actually has something to run on. Otherwise, especially when you say run cluster, you submit your jobs and you come back the next morning and nothing's happened. So this is a kind of a nice thing to add in there. So I'm going to give you again 2 minutes, so 120 seconds or so to run through this part here. So run with different set of reads. I want you to change the equals assignment to use the set operator, and I want you to use check if exists file option for the from file pairs channel factory. Oh, there's a question there. So when do you expect the first item in the tuple to be long?
Yeah, it's just a minor thing, but I would kind of expect that the 1 and 2 are used to make pairs. So if you have long underscore and then the square brackets, not square brackets, the other ones, that the first items in the tuple would be long and then the underscore, because the underscore would be part of the string belonging to.
I see what you mean. Yeah.
But it's minor, so if you don't want to bother it.
I know what you mean. Maybe Paolo's on the call. He'll be able to chime in for exactly why the underscore is ignored there. I think because the wildcard is doing something special in this case. But I know what you mean. For the gut sample, you would expect like at least the sample ID to be lung underscore or gut underscore. Yeah. Maybe Paolo can chime in about exactly how that global expansion works.
Okay, thanks.
That's a good time.
Sorry, can you repeat the question?
Yeah, the question is around when you have the from file pairs, that the expectation would be that the actual sample ID in terms of the glob expansion.
Yes, exactly.
Would be they're expecting like lung underscore would be the sample ID or gut underscore. So why is the underscore ignored? Particularly
there is a kind of heuristic here, the meaning that we just observed that is a common pattern. So to have underscore to separate the sample ID from the suffix 1 and 2. So it was just stripped for these reasons. There is no other reason. So these are just a common pattern that's being taken in consideration to remove the underscore. But the most important thing is that the star is the part that captures the expected sample ID, and then if there is an underscore, is removed.
Okay, thanks. So if you would have a dot there, the similar things would happen probably, or not? Or it's just the underscore?
If I remember correctly, only if there is underscore is removed. Other character should not be removed.
All right. Thank you.
Welcome.
Okay, cool. Perfect timing as well. The time has just gone up on that one. So let's go through and quickly do these. So the first one here is actually written for you, the ability to run this. And as I said, you can define and change the parameters. We've seen this many times, but from the command line now. And one thing to note is to make sure that these are inside these single quotes. Because this is going to do some expansion here, it's really important to put that inside those quotes. So the first example here, by default, I've got the gut. I can override that and say, okay, now run my pipeline on all the samples. This is useful. Like I want to have a really small test data set, which is my default. And then when I run, okay, I want to run on everything that I have. The next question there is going around how we can use the set operator. So the way you could have gone about solving this would be to think about, firstly, what does the set operator do? Because you don't really know, it's going to be a little bit difficult. And I would sort of select here onto the results. You can see that there's some examples of how set is used. And it's basically, it's the alternative way of saying my channel equals the channel here. And the alternative to saying my channel equals then is then to say set my channel. And it's just, it really sort of depends on whether you want to do the variable assignment before or afterwards. So we can see kind of the exercise is asking you to sort of take this part here, and you would say set, and in our case, read peers channel. One thing to point out here is that what we're doing is in this location here, in this situation, is we're chaining these operators together. So you can see we've got from file pairs, and then we're doing set. Often you'll see this done, and kind of I would say the preferred way to read this can often be like this. So you'll have these things underneath. So you could have any kind of operator here. Maybe you do like a map or something, and then you do something else that you do here. And this kind of makes it a little bit easier to understand the transformations that you're doing to your channels. So if you read them sort of sequentially in that way. But again, it's not Python, so we don't have to we don't have to specify a particular amount of tabs or particular amount of spaces. We can put things pretty much wherever we want. So again, completely up to you how you want to do that. So I'm going to specify here from file pairs, and I'm going to go set pair, which has now created this this read pairs channel, which has this name that we have here. And the final thing that we were going to do is check if exists. And this is a parameter, essentially an option that we can apply to from file pairs. We look at the documentation here around and sort of how you would solve this problem. So you would have gone to from file pairs, and then if you look at these options here, I showed you before size quickly, check if exists is one of these. And when we use check if exists, we can apply it in this situation. So we can say, comma, check if exists, and then we say true. Now, and this is something that happens all the time, if you look at, I've just saved that, and if you look at the screen below, imagine that instead of being f.fq, I thought these were like fastq, say. Typical mistake to make. Imagine I submit this to my cluster, walk away, think it's all fine, and come back in the morning. Well, in this case, I would kind of know that there's a mistake. So it would prompt me straight away before it would even submit anything. So nothing kind of matches that pattern. I would quickly do this as opposed to launching it where it may take some time to fail. And in this case, you can see the reads there. It's run through, and we have this this read pairs channel. So nothing really super special was happening in this case, other than the fact we were creating this channel, which contained these 3 samples that we have, or as many samples as we want inside there. Let's start to do some quantification. So far we have the read pairs, and we have a channel for them, and we have the index step. If we open up script number 4 now, we will see all of this kind of coming together. So we will see the parameters we had from the beginning. We will also see the log info, and then we will also see the process index that we've already gone over. We see the channels. This is the set thing over the check if exists, we just saw. And finally, we get to our quantification step. This is the most kind of tricky one that we have, but it's also say the most interesting of what happens here. In this quantification step, you can see that now instead of having a single input, like in the index we had, the index file, the FASTA file was an input. Now we've got 2 channels as the input. The first channel is the index coming from the index step above. So it's the index channel from above. The second one here is made up of a tuple, which is the ID, and then the reads. And this is exactly taken from here. Now it's important to note, if we were to do, say, a view on this, and again, I'm just going to exit. I'm just going to return the rest of the pipeline. So I'm going to say view, because we really want to see what is this made up of. I'm just going to write return here so it stops the pipeline there. When we run this, we'll see that the structure of this read pairs channel, firstly, that didn't work very well. The read pairs channel, params reads, there's a mistake here. Okay, let's remove this. It's because I'm running script number 4. Okay, so if we look at now what's the structure of that read pairs channel, we'll see that it's made up of a tuple where the first value is the sample ID, and the second value of the tuple is these files, is this path. So this is where we should match the cardinality. So the input section here should match what the channel is. Basically, the input should match kind of what we're expecting. So we are taking as input here a tuple, which is made up of the pair ID. You'll often see this written if you don't see the qualifier here. This is the equivalent of value here. And you'll see in some, it becomes a little bit more strongly required here. So this is a value, in this case, gut. The path, which is the reads themselves, which is the second part of our tuple, from the read pairs, this section here. Let's remove that. Then the task itself, what runs, very similar to before, the salmon step. So salmon quantification, we have the threads as before. Lib type, this is really specific to salmon, just the way that the library runs. You could parameterize that if you want. The important parts are it takes as input this index. So this index is a Nextflow variable from here. The first read, which is denoted in salmon, you need to write -1, first read. Now notice how we can specify what that first read is by calling it, because again, this is a kind of, it's a tuple inside a tuple. So we can call the first one here with read 0. We can specify the second one with reads 1 there. And then finally, we have an output, which is just the ID, the sample ID that we want to write to, which is exactly what we capture here inside this path. So we capture in this path the output, which is the quantification, and then we sort of put this into that. So a lot of things going on here, but let's just kind of run it first and see what runs. So let's say here, remember this, we're running on a single sample, everything's going to launch, and we say Nextflow run script 4. Okay, and you can see it's printed to the screen here. I left something in there. I'm not sure if I saved that completely. That doesn't look right. let's try it again. I don't think I saved the script before I launched that. That looks better. So now you can see that the salmon index step runs once and the quantification step runs once because we've only specified the gut sample. And that's going to kind of launch through and we see we get these two processes created. Likewise, if we wanted to look inside this salmon quant, this quant channel, and we wanted to see what was being generated here, we could quite easily do this. So I'm just going to do everything else the same, just viewing the output. And what we see is generated here is this file, it's this directory, I should say, which is called gut. And the reason it's called gut is that the output here is this sample ID, which we're taking from here. Okay. What about if I want to run this cell now, not just on single samples that I have, not just on the gut, but I want to run this on all of them. And again, I want to use Nextflow resume here. So I'm going to run as I had before, but I'm going to run script number 4, and I'm going to add on here all of the reads and resume to use the caching. Let's put this here, makes it easier. And you can see that launched. And then you can see that we've now got index running once and it's cached. We've got quantification running 3 times, one of which is cached, which was the lung sample. And then we can see the 3 outputs of that channel, which was gut, liver, and lung. And each one of those is a quantification output. It's a directory which contains the output of the salmon step. So we've kind of chained our pipeline together now. And we kind of been able to build these multiple steps together. We've run the quantification, etc. But maybe we want to kind of modify this a little bit and kind of see a little bit of other things that we can do. One thing that's kind of important, particularly when you start to run with a large amount of samples or a large number of files here, is that having this output, in this case, inside these work directories is not particularly easy. It's not. I have to remember, where is the gut sample? How can I find that? How can I use that in like my my RStudio that I want to kind of pull up now and I want to do some interactive coding on? How am I going to do that? Likewise, this kind of quantification one, etc. This doesn't really help me to know exactly what sample is using. So there's a couple of things that we can do for that, and this is what the next exercise I want you to look at is. And this is the exercise 7.4. And in 7.4, I want you to consider what we're going to introduce now what we have called directives. And directives are a part of processes. So they're kind of a part of the process that you can kind of think of as config for your process. I want you to add 2 directives. The first one is tag, which is going to give us a kind of identifier for each task. And the second one I want you to use is publish dir. And in publish dir, we're going to now think about at the very start when we created this results directory, and we thought about, okay, how are we going to use those, how are we going to store the outputs into a location that's going to be useful for us. I want you to create a publish dir for the quantification step. So you use that directive that uses our params.outdir. So again, I'll give you a couple of minutes to run through that. Click on the documentation there to see the examples of how you can use tag. And think of the tag that might make the most sense. Think of the variables that you have available to you inside of that process, which may make the most sense. I'll give you again another couple of minutes to do that. Okay, hopefully you're able to give that a try, and even if you didn't get it to work, at least kind of get an idea of what's happening there. So I'm going to show you very quickly how we can use these. In the first case, tag. So I'm just going to open this in a new window. Can close these other ones here. With the tag itself, it's really a useful way to apply any kind of custom label. And in this case, you can see that we're using a variable, so $code, which is taken from the input, which will then allow you to see when you submit this, the actual individual value here. So in our case, it may have made sense for you to be able to say inside here, so below, is where all of the directives get placed. we say tag $, and then I'm going to put in here peer_ID. And this peer_ID, this could be your sample ID, this could be whatever you wish. Now each of those tasks, when I run them, in the first case, are going to have this, this ID here. The way that we're printing this to the screen is kind of more set up for production usage, where you have hundreds of, where you really have sort of hundreds of samples for each process, and therefore it's going to show you the process like kind of over the top of itself. So there's actually three tasks for the quantification process, and you can see that we're using the gut. Only the gut one is actually being shown here, but the other ones are underneath, so to say. You can actually turn this off and you can define it so it shows you all of the processes if you want. The other one that we're going to look at and probably the most important directive, or one of the most commonly used ones, is this publish dir directive, so publish directory. And this is a way to capture the outputs of our tasks and place them into a location that we're going to use later on. So this publish dir, in this case, you can see the documentation for running this is that you place, you write publish dir, and then you specify a location that makes sense. In our case, I'm sort of given what I said before, we could also use the one that we defined above. So remember, we had params.outdir, and then you could leave it like this. So if you just wanted all of your results to go into that location. But what it could be useful to do is maybe to say where you want the result. Maybe you want to have like a directory inside of that. And in our case, maybe this is the quantification. So we want all of the results related to here to go in quant. Now you could do the exact same thing with here. I'm going to go up this and up here and do this in the index step. And maybe I want my index to go into index. So now when we save this, I'm looking here, I'm going to save this file, launch everything exactly the same. You can even use resume here. And if we look now, what's going to be created in this case, if I do tree on results here, because remember that outdir is pointing to results, then we'll see that we get the index, and the index itself is inside of that directory. And then we've got another directory inside results called quant for quantification, which contains the gut, the liver, and the lung. So this is a way to organize the outputs of our pipeline so that we can access them in a kind of more user-friendly way without having to remember which work directories all of these things are in. I should point out that, remember, because outdir is just a parameter, I can run the same pipeline and be like --outdir results, horrible results number 2, and we print this and we run this, and again now this will actually just place those results inside results 2. Okay, so I'm just going to do tree on results 2, and you can see kind of how that works there. Okay. Another thing that we can do here is actually do kind of options on those directives, and particularly publish dir is a really useful one, so you can define what's happening. If we do tree on those results here, you can see that again it's symbolically linking. So it's actually just pointing to the work directory where this is. That may be useful, but you may also be in a situation where you want to remove your work directory. Maybe it's just like a temporary location for the intermediate files. And in this case, you can do something like mode. So you're going to modify the way that this publish dir works. And you wanted to actually copy, say. And by doing this, now you're specifying, okay, instead of just symbolically linking, which is the default here, we launch this. And now here, in fact, I may need to remove the results first. We'll see what happens. Let's remove our results first. Otherwise, we're just trying to copy over, which is not going to work. So mode copy and run. Okay, that is correct. One of the options is actually overwrite, so I could have specified overwrite as well. But by looking at now tree results, now instead of being a symbolic link, you can see it's the actual, the quantification step anyway, is the actual files, the actual quantification files. It's not symbolically linking the gut, etc. It's actually moving those files and copying them to their location. And you have a whole bunch of options the way that that works there. Okay, I think that's it for that step now. Let's consider now the next step that we're going to go on to. And so far we've just been looking here at script number 4. So let's move on to script number 5. This is not a big one, but it's something that we can kind of go through a little bit quicker. And what's happening with script number 5 is we've now introduced a third process. So everything's the same as you've seen before, indexing, quantification, etc. This third process now is going to do something relatively simple. So it's actually taking the same input as before. It's taking the same read pairs channel. Notice this read pairs channel. It's exactly the same as this one here, which is exactly the same as this one here. So it's actually just trying to use that as input. What's happening in terms of the script section? So it's making a directory, which is going to contain fastqc and the logs of fastqc, and each of those directories will have a dynamic sample ID taken from here. And then it runs fastqc, and it's just putting the output, the logs, inside of that location. And the input of fastqc in this case is the reads. So the reads themselves gets generated there. It's kind of pretty standard. The output here is going to be the logs themselves. So you can see that you can also create output dynamically. So this is going to, the output here is just the directory that we are making in this case. But the important point of this exercise is to consider that when you have the read pairs channel here, and because of the way that kind of data flow programming works, you can't what's called consume the same channel twice. When an element, in this case, a pair of files or pair of reads, enters into this quantification step, basically when it comes from this read pairs channel, it's consumed. And this means that if we were going to go run it and try and use it again, it doesn't actually exist. So if I say Nextflow run here, I can get rid of all of this. I'm just going to run script number 5 by itself. We don't need any options. And try and run script number 5 and see what happens. You'll see you get this error. And the error there is saying that that read pairs channel has been used twice as an input. So read pairs channel here has been used as an input both here in the fastqc step and in the quantification step. Now, in what's called DSL2, which is the kind of the next iteration of the Nextflow language, it's a very subtle syntax change. This actually doesn't occur. So Nextflow looks ahead for it and it fixes that, basically creates a duplicate of that channel for you. But in the kind of strict sense of data flow programming, what you're supposed to do here is actually just duplicate this. So I take this, instead of saying set, which is to create the ID for the channel, I turn this into. So I can say into read pairs channel 1 and into read pairs channel 2. And again, this is something that just can maybe catch people out. Hopefully the error messages are kind of good enough here that you are able to identify that. So you can say read pairs channel 1, read pairs channel 2. And from there on, you're kind of fine to go. Just confirming that. And you can see that that's now running quantification and the fastqc on both of those steps. Okay. Let's bring this all together now before we take our final break. And what's happened so far, I want you to now run sort of script number 5. So I'm going to go, and I want you to now to run that though on all of the samples. So this is still running on all. So I'm going to say script number 5, and what's the easiest way to do it? I'm going to modify my script number 4 here because I don't need this. I don't need this. I'm just going to run script number 5 on all my reads. So here, Nextflow runs script 5, pointing to all the reads. And make sure that's saved. Can close some of these ones we don't need anymore. And launch this. So we can see that index runs once as expected. Quantification is going to run 3 times. And the reason the quantification runs 3 times is that we have 3 samples. Likewise with FastQC, we have 3 samples. Remember that channel contains 3 elements and therefore we get 3 executions of it. For our final step now, we want to create a report. And to run a report, we don't necessarily want to create, we don't want 6 reports. We don't want to run multi-QC 6 times. The way that multi-QC works, and something I'd sort of recommend checking out if you're into this, is multi-QC has a kind of very smart way of generating reports from over 100 bioinformatics tools now. And the way that it works is you just specify, to run it, you specify multi-QC dot, so multi-QC here, and it looks for all of the logs that are in that location and generates a report based on that. We can use that inside Nextflow pretty easily and kind of quite successfully. But there's a caveat. As I said, we want to run multi-QC once, and we have, in essence here, we've got 6 inputs. We've got 3 quantification inputs, and we've got 3 FastQC outputs that we want to kind of use into our multi-QC report. Well, one way, if we did this a kind of naive way, would be considering what do we have here? Let's look at the FastQC channel, .view. We've done this a few times before, viewing our outputs, and our quant channel. .view. You'll see that we have here 6 elements. I could run resume on that. Apologies, I'll run resume from now on. I'll speed that up. But each of those kind of 6 elements is now in 6 work directories. So they're all kind of split across there. And what we want to be able to do is kind of pull all that together into a single report. If we look at now, I'll just let that run, but you can see this is the 6 that are generated, again, from 6 working directories. If we look at what we can do now, we really want to create multi-QC. And I'm going to pull up script number 6. And script number 6, we start to see how we can use operators to modify the contents of the channels, in this case, with these files here, and kind of do something with them to kind of pull them together. So we have everything as before. And the final thing that we have here, though, it's a little bit funky. So we're going to say multi-QC. And what we want to do is we take multi-QC. The input, though, becomes the quant channel mixed with the FastQC channel and finally collected. Now, let's kind of break this apart before we run it. What is this? Well, let's go look at the example above. So what is actually generated from here? Let's copy that, go into this section. The quant channel mixed with the FastQC channel. Let's do that first. What actually happens here? So let's view the output of that. And again, you could write this as this here. I'm just running script number 5. I'm going to add resume here. I just added in this, what we call this operator here, which is this combination of these, combining 2 channels together. We're doing that. So now we have what is a single channel. We can think of this as our set here. You could say something like multi-QC input channel. This is creating a new channel which contains that. So just to prove to you it's a single channel, we have this. Okay. Let's launch that. Everything, I haven't rewritten it in different syntax, but everything exactly the same here. So this channel now contains all of this, 6 elements. When we run here, and this is the kind of the special part, when we run on this, that we want to say, in this case, collect, instead of having 6 elements, in that channel, we collect all of the elements into a tuple which contains all of them. We collect them. It's like the opposite of flatten that we saw before. So now when I run this, we've taken the 3 inputs from the quant channel. We've taken the 3 inputs from the FastQC channel. We've first mixed them, which is the equivalent of concatenating them. And then finally, we've collected that concatenation into a single element, which contains all of these logs into a single element itself. Now, going back to multi-QC, how do we use that? Well, we just say multi-QC dot. And all of these files you can see here in my terminal are now in that single task directory. So as a user, or as a launcher of this, I'm going to say Nextflow run. I'm going to modify this. Instead of running script number 5, I'm going to run script number 6 here. And we'll see that when we launch through this, multi-QC runs once, and we get 1 report generated from that multi-QC report. Okay, that's a lot of information there, and that's kind of, it's quite diving deep into that. What I want to see, and one thing that we can do sort of quickly before the break is, can anyone guess what would happen then if I remove this collect? What's going to happen if I run this now?
I think multi-QC and all the files separately.
Say again, sorry?
Multi-QC on all the files separately.
Exactly. So what's going to happen if we run here now? Instead of having multi-QC running once, multi-QC will run on each of the files. So we're going to get 6 multi-QC reports, which is obviously not what we want. So here again, you can see that we're manipulating the contents of the channel and manipulating the elements to kind of drive the execution. And this is a kind of probably, as I say, the most difficult thing to get your head around the Nextflow, but once you do, it's the most powerful thing, because it means that we can write very simple expressions for mixing, combining, modifying, mapping, and all of these, which are what we call operators. There's something like 50 of these things. And this is the way that we change the data, that we manipulate the data, filtering, transformations here, splitting, combining different things together, forking, and as well as some other operators. All of those are really powerful because they work at scale. They're not iterations. They're reactive using this channel concept. Okay, enough on that. We'll see more of that tomorrow and more examples of that. And we're kind of getting towards the end of the time for this section. The last thing I wanted to show you was around script number 7. So if you look at script number 7, you can see that there's ways that you can do things, say, in a data flow model. So like, instead of having to have things like all of these processes which run, you can have something like on complete. And this is a way of saying, at the end of a pipeline, print something. So in our case, we do the exact same thing. Here I'm going to run script number 7. And if when the pipeline is complete, if it's successful, print me this message, like open your browser here. If it was not successful, it's going to basically point somewhere else. Another thing I want you to see is, like, notice how that I ran in script number 7, and I've never run script 7 before on this machine, or on this virtual machine. But by using resume, all of the tasks were still cached because nothing really changed in the task, even if it's a different script. So that kind of, again, highlights a little bit of that, how the caching mechanism works. Because those tasks existed in my work directory, then it was able to do this. Okay. There's a question, sorry, I missed that before, but if DSL fixes the syntax, how much of today's lessons would be applicable for DSL2? Everything. So everything, so I mentioned very quickly on DSL2 is it's actually completely the same underneath. It's just a slight syntax change of how you can, really for the modularization of your pipelines. So all of the concepts are exactly the same. Everything's identical. The syntax changes ever so slightly in the way that really the only thing that changes is that you remove these sections and you reference them outside the process. But we'll see that later on tomorrow as well. The concept is exactly the same. Last thing before we take a break, I think this is kind of super cool. So far, there was a question before about the project directory. We're running like local files so far. So everything, this is like a .nf file in this local machine. This is all of that. But what happens if I want to go run something from GitHub? And we mentioned before, everything should be a Git repository. How can we launch the same pipeline from GitHub? Well, one way that we can do that is firstly, we can find that pipeline. And if you go and search for Rna-Seq NF, you will find a couple of pipelines. Next one, right? Let's find too many. Okay. I want you to find, and probably want to do GitHub as well. I will put this link in there. And there's also a couple of links to it in the documentation. I want you to find this proof of concept Rna-Seq pipeline. So I'm going to copy this and place this in the slide. Okay, that's in there now. And what I want you to do is take this Git repository. So this is just this. I'm going to take the Git address, like the HTML Git address. And you can see that this pipeline is essentially the same pipeline. There's a few tweaks to it, but it's the same pipeline, same processes, etc. I'm going to go Nextflow run. And instead of specifying like script7.nl, I'm just going to specify the Git repository. And finally, I'm just going to say with here, Docker here.
I'm not sure I understand.
Siri, again, I'm going to turn that off. I'm going to say with Docker here. And let's see what happens when we run this. You can see we can launch this here. So hopefully this works, I haven't tested this, but you can see it launched. The first thing it does is it's going to pull it from GitHub. So it's downloaded this from GitHub. It's printing to us very much the same as that we had before. It's printing the same output, the transcriptome, etc., and it's running through the same steps. Now, this is actually in DSL2, so it's sort of looks slightly different here in terms of what these are, but everything is exactly the same. We just ran something from GitHub that completely independent. It could have run with different containers. It could have been run from anything. So that's the kind of power of the ability to kind of combine containers with GitHub and kind of pull this itself. And this is a kind of really useful feature to be able to do. So I'll just copy that into the chat in case anyone is missing that command or wants to see that. The question then was what is published dir? And sorry, what is base dir and why is it important? And I just want to show you here the question. There's a question, could I exchange parameters and use my own FASTQ files? Absolutely. So we could be, let's have a look as we go clear. So let's go everything the same. And now let's actually, instead of running on the project one, the one from GitHub, we could even say reads, and let's go data. So let's run like the pipeline's coming from GitHub, defining the container in our Nextflow config, and we're going to pull the reads from a location that we have. So data gggal dash reads, star underscore 1,2 dot fq. Let's put those in quotes. Now, again, we're running from GitHub, but we're launching now on our local files. Okay, something that have matched there. Not sure where's my error here.
You have an extra reads in there.
Extra.
There is no reads directory, right? It's ggal and then the
yeah,
blob.
you're right. Perfect. Awesome. Thanks a lot. That's useful. Yeah. And so we run here, and now I'm kind of combining these things together. So you can see that will run through, and it's running on my own data now. So pulling something from GitHub, running on my local data. There's an option now, will resume work. With the cache option will resume work as well if you use resume. In this case, there are subtle differences in the pipeline. So it wouldn't work. It wouldn't have worked the first time I run it. However, if I say -resume now, and again, this is -resume on the GitHub version, it's going to do exactly the same as before. So it's cached. The caching works identically. So you can see that all of those will be cached there. And the final thing I was mentioning was that they have this script number 1, and we had this base dir. Why is that base dir there? And the reason that the base dir is there is that this location is now, where is, like, you know, we pulled that from GitHub, but like, where is it? And the where it is actually in this location called .nextflow assets Rna-Seq data gggal. So it pulls a copy from GitHub, right? And therefore, in this case, base dir is actually this location. Okay, and that's the subtle difference. So when you run from GitHub, it basically means when you run from GitHub, it works because it knows the base directory of where the project is itself, as opposed to, and you can kind of see here that this transcriptome is actually in that .assets location. From a user perspective, you don't need to remember that. You just make sure that you put base dir, and then you put, you know, the stuff which you're going to put inside the Git repository, some small sample sets, etc. Exactly like that. Okay, I think we've probably gone 15 minutes over time in terms of taking a break. But let's take a break now, and we're going to finish off then with the container section, and we're going to see how we can build that container that we just used now. So that salmon container that we've built. It's not a long section, so we should still have plenty of time. So I'll see you back here at 25 past the hour. So that in Central Europe, it's going to be 8:25. And we'll jump into that. And if you have any questions, save them up, and I'll be back there, and we can chat about that. Cool. See you soon. Okay, so the question about how we've been continuing on with chapter 8. Just have a look exactly what the numbers were, what we've been doing. So far we got up to number 7. We basically finished all of 7, and we are up to section number 8. I'll also say that all of this material is online and available all the time, so you don't need to kind of worry about it kind of going away or anything. You'll have access to it all the time. So we haven't actually started on number 8, so I think it's Gabby, if you're joining now, you can follow along with us as we go. So let's finish off today, and you know, thanks a lot for making it this far. I know that's 4 hours of Nextflow. Particularly, I don't know where you are. It's pretty hot here. Can sometimes get to it. So let's just jump into something a little bit separate from Nextflow specifically, and see how we can use and build and dive a little bit deeper into what's happening when we run with containers. Hopefully this will be useful outside of the context of just Nextflow, or even outside the context of workflows themselves, and going to get a bit of appreciation for what happens. So we're going to start with looking at, and we're kind of going to, most of this is going to be around Docker, but the principles are exactly the same typically for the different container runtimes. And if you're kind of sort of familiar with containers, and maybe the context you've seen them in is maybe typically in bioinformatics, but containers were not and really have not been designed for bioinformatics, or really for pipelines more generally. They're really something which came about from use of really typically like developing web applications, so like long-running services. You can think of things like your front end of a web application or a back-end application, and those kind of containers themselves were sort of developed and took over the role of things like virtual machines, which were spun up, or actually just installing the software on a virtual machine itself. So what are the benefits of using the containers, and why do we consider them? So let's have a quick look at section number 8 at the beginning of this. So hopefully I'll share my screen if I'm not already, making sure that. And then in section number 8, you can see we are using containers for dependencies. And what I mean by that is, like, we often have dependencies inside of our pipelines. Example before is that we used FastQC, which was a tool which was not installed on our machine. We used Salmon, we used MultiQC. All of those are dependencies. They're software which our pipeline depended on, that we were able to put inside of a container and use in that way. So managing these dependencies can often be very difficult. And I mentioned at the very beginning of this that often this in bioinformatics, you spend a ton of time just installing these tools before you can even use them. And containers can, in theory, eliminate a lot of that for you if someone's already done it before. And what we're going to look at now is, and start with, is going to build our own containers themselves. So containers came out of what was called Linux, these control groups or C groups. And then Docker came about, and Docker was a kind of company early on in this. And I think the first talk of this was, sort of release of this was 2013. So yeah, getting on only 8 years ago now or so. But at that time, it kind of really revolutionized what you can do with containers. And Docker was, kind of came out with the tooling which made it easy to do so. And because of this, the kind of Docker standard has become the kind of primary way of dealing with this, even though there's many runtimes that use the same thing. There's actually something called a container, I think there's an OCI, which is a kind of open container initiative standard for these containers themselves. Enough about that. Let's think about what we can do these things practically. And running kind of a Docker container is fairly trivial in itself. So I'm just going to close all of this, and I'm going to run, and now I'm just going to say, I want to run a Docker image itself. So let's run the typical hello world example. And to do that, we can say Docker run, a little bit like Nextflow run, and we can say hello world. And what's nice about this example is it kind of tells us a little bit when we run this, what's kind of going on with Docker and what's happening in this regard. So the first thing that we can see is that we run Docker hello world. It's unable to find the image locally. This is important. So it's unable to find this locally. So it's pulled it from remote. And if you think back to what we did in the very last thing before we left, where we ran our Nextflow pipeline remotely, that's exactly the same, where we're pulling it from a remote repository, and it basically knows that it's not local and being able to run it on the fly. Now, the next thing that's happened here is that it's downloaded that image itself, and we get this kind of hash, which is a digest of the image, essentially a unique identifier for it. Then what we get is this message which is being created. So the thing to remember about Docker, and the thing to think about Docker and sort of positives and I guess negatives of it, is that it's not simply a single client in itself. It's not like Nextflow, which is just like running the Nextflow command line tool. Docker itself has a client, which is what we're writing, the tool we're using here when we say Docker run, but it also has a daemon. And that daemon is basically a service which is on this virtual machine or on your virtual machine, on your own local machine if you have Docker installed, which is always running. And what's happening is when we're saying Docker run hello world, that the Docker client, so the command line tool, connected to the daemon, to the service, the daemon then looked for, is that file, is that container, say here, is it on this machine? If it's not, I'm going to pull it remote. In this case, the default remote registry here is called Docker Hub, kind of like GitHub. And then it's going to now create that new container image from that remote. And then the daemon is basically what's running the container, will stream the output to that client, which is exactly what we see here. When we're seeing this message, which is the client kind of streaming that from the daemon itself. So why is it important? Well, we'll come to a little bit later about why that's important. But what we can also do now is start to run some slightly more complicated examples. So this is pretty trivial, because if we have in this case here, it's really just printing this to the screen, not really useful. What about doing something a little bit more useful? Let's try and now pull a container. And I'm going to pull a container that is now, instead of just being a hello world example, is actually a full operating system. It's something that we can use. And what I'm going to do here is I'm going to say Docker pull Debian. So Debian is a little bit like Ubuntu, if you're familiar with Linux, and it's a kind of just a flavor of Linux. And the nice thing about containers is that they have what's called layers to them. And we can start with a base layer, with a base image, which we can then build on top of. And in this case, we're going to start with Debian Stretch, which is basically a operating system, and Stretch is essentially the version of that operating system we're going to use, and we're going to build on top of that. So now I want you to say Docker images, and I want you to see that now we've got 3 images. And if you remember from before when we ran this, we have the Nextflow image, which we used which contains salmon, multi-QC, etc. We've got the Hello World one, and we also have this Debian one that we've just run. Okay. How can we now kind of do something a little bit more useful though? So far it hasn't done so much. We've just printed that message to the screen. We can interact with this container. We can jump into it doing a similar command, except when we run docker run, we can do -it and then the name of the container, in this case Debian. And we'll put the whole name here. Now, oh, this is a typo there. Okay, let's run this. I want you to notice that you can see in the first case here, I'm Chris ISCB 21, and then in the second case now, I'm now root. So I've jumped inside that container. I want you to consider also this. If I do ls inside the container, you'll notice that I have this as the directories that I'm listing inside that. This is the location that I am. If I do pwd, you can see I'm actually on the root location of the container, and I'm also the root user. So if I say who am I, you can see I'm root. If I exit the container, and if I say who am I, I'm EC2 user now. So here you start to see some of the kind of a little bit confusing things is that like I can jump into this container and I can be root, but also the container itself has got its complete own file system. And this complete own file system really makes it like a self-contained environment. Likewise, before, remember when we said like salmon, we didn't have it, but we could jump into the container and it had its own environment with salmon installed into it. So very kind of quick kind of very basics on how we can do that. So that's that docker run IT command, which can be super useful for jumping into a container, experimenting with it, and running it how you like. Let's do some bioinformatics though. Let's try and now build some of that software that we used in the pipeline before inside our own container. And the way that we build these containers is what's called a Docker file. And a Docker file is a list of instructions on how to build a container. It's like a recipe. It's like a kind of a build recipe for building that container. What I'm going to do here, and this is something I recommend for when you build containers, is to build them inside their own directory. So like what I mean by that, like making a directory called Docker. And the reason for this is that there's a context which gets built, and the container will sometimes pull in everything that's inside your file. So you typically want to go inside of the Docker directory here. So I'm just inside that directory where I'm going to build this. The next thing that I'm going to do is I'm going to create a file here. You can do this with Vim or like Emacs or whatever your editor is, or you can create a new file. Like I'm going to say new file. And I'm going to call it, first I'm going to save it as. The important thing to note, I'm going to save it inside this Docker directory, but the important thing to note is it has to be called Docker file, and Docker has to be a capital D. So a little bit like a make file, where the make file has to have a capital M. So we're going to call this a Docker file here with a capital D, save that, and now let's think about the instructions which should go inside of this. Well, I mentioned before that these containers can have layers, and the first layer that we typically want to start with is some kind of operating system, some kind of base container that's got that information. And if you go over to the notes, if you look at 8.1.4, so going over to here, you'll see that there's the first lines here of our Docker file that we're going to use. I'm going to copy these and then sort of explain a little bit about what each of them is and place them inside my Docker file. Docker file here now starts with Debian stretch. So this is our base image, we call it. We're basically building everything on top of this. And the way that it works is each of these is sequential. So there's an order. So starting with from, adding some metadata, which is maintainer. You can put your name in there, your email. The next is the run command. And the run command is very much like being inside the container and just running those commands. So apt-get is a repository manager way of basically installing software. If you're familiar with installing software inside Linux, you should be quite familiar with using apt-get update and then apt-get install. And install, we're going to install two pieces of software. One is curl and one is calce. And finally, we're going to change an environment variable inside the container where we're going to add something onto the path. So 4 layers that we're going to do here. So four steps. I'm going to change this and put my name here so that if, say, I post this or I publish this, someone can find me on the internet and complain where I've done it incorrectly. And then I'm going to say now Docker build, in this case. I'm going to give it a name. I'm just going to call mine my image. And then I'm going to say dot. And this is why I'm building this inside its own Docker directory, because I don't want to build everything else in that. So I'm going to say Docker build -t my image. And you can see it runs these steps. And the first step was very quick because it's taking something container we already had. Obviously, the maintainer step, this metadata is very fast to add. The third step takes a little bit of time because it's going through and doing the apt-get update and install. And the fourth step, again, is very quick, this environmental variable. This container is now built. My image latest is available. And if we were to say Docker images, here, we would see that this my image is now available for us. And you can see we created it 23 seconds ago. In terms of size, well, it's not too big. It's about 130 megabytes. You can see that the Debian itself is about 50. The Hello World was 13 kilobytes, so super small. And the actual Rna-Seq pipeline one was 2.5 gigabytes. So kind of see the whole spectrum of these containers here. Obviously, getting them as small as possible is useful, and there's a whole bunch of sort of techniques and stuff on how you can do that as well. For our purposes, though, now we've kind of built that first container, and we might want to say do something with it. How you run these containers, or I showed you before that there was a way of running them interactively with the IT. I want to see like how we can say use some of this software. We've now installed calce. I don't have calce on my host. I don't have calce on the local machine, but I do have calce on the container. And I can use that application by saying Docker run, pointing it in my image, and then saying everything else after this will just be executed inside the container. So calce hello Docker. That calce hello Docker has been run inside the container. This does not work if I run it here, as I showed you before. So calce doesn't work. Command not found. Exactly like before we had salmon, which is command not found. So now we've kind of built the container. We've seen how we can add different layers to it. We can add steps to it, and we can kind of run these things and start to use some of the software itself. Okay, now let's add something a little bit more useful. Let's add salmon itself, because we want to run salmon. And there's a couple of ways that you could do this, and I'm not going to show you the kind of final way to do this, but one way of doing it would be to download that from GitHub and then kind of add that in our container and put it on our path, basically install it inside the container. And inside the instructions here, you'll see that there's a fifth line that we can run. And that fifth line here is this curl command, which is pulling it from GitHub, and then it's moving that those binaries into our path. So I'm going to copy this, place this on the end here, and then I'm going to run everything exactly the same. So I'm just going to run exactly as I had before with Docker build my image. And what's interesting here is you'll see that the first 4 steps are all cached. It's a little bit like Nextflow's caching mechanism. We don't have to run all those through again. We just run the 5th one, and it was relatively quick. And we've now updated my image And the other thing to notice here is that if I don't put what's called a tag, if I don't put like a specific version or a label on it, it's just going to use latest. And these tags are mutable, so you can overwrite them. So something to keep note of is that now this image is different from the one that we had originally. We can also see that now by doing as we did before. Instead of saying Docker run my image calce, I can now say Docker my image salmon. And you can see that salmon's now installed on the container. So relatively easy. Okay, that's our kind of basics of building a container and how we can do it. But how can we use these things now? And how can we start to think about using them in bioinformatics? And this is where things start to get a little bit tricky because for several reasons. I want us to think about the first script that we ran in that pipeline before, script number 2. And if you can't remember that, so that was the one that we had in script number 2. Let's pull that open. It was a single process. So it was the single process here. And the bit that we're interested in is salmon index, where we're going to specify the transcriptome, basically going to specify an input and an output. I'll remove this for now. So this is what we want to run. We want to run this inside our container. Now, I'm not going to use Nextflow, obviously, because we want to try and see exactly how this works. Okay, how are we going to do it? Well, the first example you might just think would be Docker run salmon index, kind of trivial, and then say point it to the transcriptome itself. So I'm just going to cancel here. What I'm going to do is going to go back one because I want to be in the same location that I am that I'm normally in. So let's go here, cd back one, and I'm going to run exactly as before, Docker run my image salmon, and I'm just going to go index, and I'm going to say inside of this index, we're going to say the transcriptome. So if we remember before, it was like data dash ggcal, and it was dash transcriptome. I think you can find it there. And then we're going to say dash I index. Everything's the same. Let's run. Okay. So that launched, but first of all, it's seen one error. One is that I didn't include the option transcriptome. So I didn't actually say dash T, which is correct. So dash T. So it's kind of, you can see that salmon's running here and it's picking up my errors. The next error it's giving us is that this file does not exist, which is kind of weird because if I go here and if I say ls, the file does exist. So what's happening? What's happening is that the container has got a completely different file system. So that transcriptome is not available to the container itself because they're completely separated in this regard. So how can we fix that? Let's go back and see what we ran. One way we can fix that is what's called volume mounts. And volume mounts are a way of taking the basically mounting the file that you have inside the container. So we can do this using the run command here. And there's I think there's a couple of shortcuts to this, but basically one is saying dash dash volume. And here you specify the file that you want to mount. So in our case, we want to mount the transcriptome. So I'll just put the full path here of the transcriptome. And then you say, where do you want to mount that file? Well, we can just mount it on the root under transcriptome. So the root of the container this is. Okay, finally, I'm just going to specify that this file now is now in the root because this is now the location in the container I have to specify. Let's run with this. Okay, so this does not exist, so I've made a mistake somewhere. And what mistake am I making? Oh, it's a little bit hard to read. I think I'm doing a typo somewhere. Transcriptome. Transcriptome. It's a little bit hard because it's split across the screen. Let me copy paste my Let me copy paste my commands from before. Apologies for that. Okay, it's going to run the same thing. Just copy paste. So here, oh no, not that one. This one here. So now I'm going to run the same thing as before. And you can see that the command that we ran here was I've just used the volume mount to mount the transcriptome on that location. And then when I'm running salmon does index, I'm specifying the location in the container. And this runs. So you can see that this runs through. And this is kind of the output of salmon when you're doing the transcriptome. But there's one problem here is that the index that we're expecting. So if we remember what that command is, this index, this transcript index that we've created, where is it? Is it gone? Again, the problem is that the container's gone up. It's mounted with this transcriptome, run on that file, but now the transcriptome index it's created is inside the container. And the container shuts down at the end of that, and that file is lost. So containers are immutable in the sense that when you start them up every time, they begin in the exact same state they were built in. So they're kind of guaranteed this kind of reproducibility, but it means that anything that you build, anything that you run in them, as soon as that container's gone, you've lost it. And the way to get around that is to, instead of just mounting our input files, what about mounting our whole home directory? What about if we mount now actually the whole host inside of the container? And that way we can get around this problem of them having different file systems in different locations. So I'm going to do the same thing as before, and now I'm going to change, the only thing I'm changing now is my volume command. And my volume command here is now going to be, instead of being home, instead of being the specific transcriptome, it's just going to be home. And I'm going to say everything else the same. So I want to create this index here. You can still see it's the same command as above. The only other thing I'm doing is I'm specifying a work directory. And this is not like a Nextflow work directory. This is a kind of the work directory of where we're going to be running this command. In this case, it's pwd, so here. Launch that. You get exactly the same as before, except for one difference. And that one difference here is that now if we look at ls of index, now the index is actually being created. So that's all, it's all good. So now we've basically been able to run that command. We've been able to mount the input, and we've been able to find that. Still one problem though. If I do this, see if you can spot the issue with the index that has just been created there at the bottom. The issue there is that that's been created as root. And when Docker is running here, Docker is running as root. And this is kind of a problem as to why Docker is typically not used in shared systems like HPCs, because Docker allows the user to elevate their privileges, to elevate themselves into root. And this obviously has, a ton of problems to be able to do. So if you think about that, that's kind of why people sort of move towards like Singularity, because it doesn't have this daemon process which is running as root to launch. Everything else is the same though, and I will show you in a moment that we can use our Docker files in many locations. All of this was a very long-winded way for me to say, don't do this. This is obviously insane because no one wants to write that inside some massive amount of bash scripts and kind of chain all of this together. And this is where we can go to the same thing and we can say, okay, clear this. I don't want to run this. It's way easier to say Nextflow run script 2, specify with Docker if we want, but you can put this in the config, and we just say my image. And here, if this is worked correctly, we should now be running Nextflow itself using our image that we just created. Final thing on this is what's happening there? Why are we just able to run Nextflow so easily just by saying with Docker? And now that we've kind of seen a little bit about how Docker works, how Nextflow works, we can see what Nextflow does when it runs every task. So this is just one task, but you imagine you have tens of thousands of these and it kind of runs in the same way. if we cd into their work directory, into the C0, etc., B3, there is a file in here. I showed you before, the .command.sh. This has the actual, the part which gets executed, the kind of script, this part within the triple quotes. If we were to look at that though, and we were to say, okay, cat on this other one, which is called the .command.run. Now, you don't really need to go into this ever, really, but I just want to show you what's happening inside here. When we do cat.command.run, this is what Nextflow executes. Nextflow turns, and I want you to look at this launch section. Each task becomes a Docker run command. And it becomes a Docker run command with the CPUs that you require. It mounts the volume. So you can see here, it's mounting the location that we're launching this pipeline. It's also mounting the PWD. So the PWD in this case is the working directory. And it's also here going to create this working directory for PWD. It creates an entry point on bash because we're running a bash script in this case. Here, it changes the user so that the Docker user in this case is the user of the host, not root. So it kind of fixes that problem for us. It has this name. It also uses now the image that we specify. And then finally, it actually runs this .command.sh inside the container. So a lot of that is kind of all taken care of taken care for you by using this approach here. Okay, so that's just a little bit of a deeper dive into it. But for most purposes, we can just remember, specify with Docker or Docker enabled and point it to the container that we want. The last thing, the very, very last thing, how would I recommend that you do this in practice and kind of what that looks like in real life? Well, there's sections in here, and you can read this later on, but there's a whole bunch of tooling which exists, and what we're able to do is essentially Singularity, which is another one of these runtimes typically used in HPC. It's actually able to run Docker files. So if you create a Docker file, you can run with Singularity as well. And likewise, you can just simply say Nextflow run script 2. You could even say something here like with Singularity, and then you can point it to even a Docker file here. So Docker my image, and this way works. So that means you're kind of built in this regard. Other thing that you can do, and kind of going back to the pipeline that we had before, because it's a nice example of this, is that we can leverage Conda here. And Conda is a fantastic resource for like so many of the tools. There's like 7,000 bioinformatics tools, at least inside of Conda. So we kind of want to get the best of all of this. We kind of want typically the best of Conda in the sense that it's got this fantastic repository of tools which are really easy to install. If you're familiar with Conda, it kind of looks like this. So you basically specify, I want to install Salmon, FastQC, MultiQC. Perfect. I want these versions. I mean, this is like the epitome of trying to make things easy to do. It has some problems though. It's slow to install. Conda itself is not a container. It's not like you can tell Aws Batch or your cloud service or maybe even your HPC to go like run this Conda environment. But what you can do is you can specify a Conda environment, and then what we kind of see as like a really best practice here is to have a Docker file, and that Docker file simply pulls in the Conda environment. So you just build a Conda environment inside of your Docker file, and from there you have now a Docker file, and you have a Docker container which runs on Docker. The Docker container also runs on Singularity, and then you also have a Conda environment for people who maybe don't want to use a container engine. So you're really covering all of those things with two files that you have, and this kind of provides a ton of portability. And of course, Nextflow has the ability to run with all of these as well. So you can even say, instead of saying with Singularity, you can say here with Conda, and then specify a Conda environment. Okay, I think that's pretty much it for us, and that's kind of good timing on all of that. So where we're going to kick off tomorrow, there's a few little bits of information here around running Docker files, Singularity, etc. But it's kind of more on the specifics. What we're going to jump in tomorrow is Paolo's going to take over, and he's going to go a bit deeper into the syntax and really start off with the channels themselves. So diving into the different ways you can build them, what they're made out of, the processes, which is section 4, and kind of the meat of how you build these pieces up. He'll also look at some of the operators and the kind of ways that you can pull those together. And then I think one of the most fun sections of this is then we'll jump through to the Nextflow configuration. We touched on it a little bit with the Docker files, etc. But and we're using Docker, but the full kind of Nextflow configuration, the different scopes. So we've seen params, but jumping into some of the other things that you can do with environment variables, etc. And then we want to consider, once we understand the config, and the main part of the config is like deploying in different environments. So deploying into your cluster, how can you run these pipelines now into Slurm? What do you need to set up? What do you need to do? How can you take the same pipeline and run it into AWS? And then there'll be there's a few other notes here. For example, if you're interested in how Resume works, there's a kind of a bit more of an explanation around that. And error handling as well. So if you kind of want to debug things a bit deeper, some strategies for that. If you've joined late, I will just post in there now the schedule of all of this, because the schedule has also got all of the different links to the different sections that we covered today, as well as all of the timings. And other than that, I will let everyone get on with their day, and I'll be back tomorrow to introduce Paolo and Maxime. But I'd like to thank you so much for your attention. I know 4 hours of Nextflow is, as I say, it's a bit intense to do, but it's really appreciated the feedback. Really love the questions, and I hope you got something out of today, even if it's that you can use containers or pull from GitHub or something. But thanks a lot for your time, everyone. I'll stop sharing my screen now. If you have any questions, though, if you have any questions on the stuff from today, I'm happy to answer those questions first up tomorrow as well. We can go over any of that.